โอเคผมถามพี่แอดมินแล้วเขาบอกว่าให้สอนภาษาอังกฤษ
อาจารย์ครับเพื่อนผมคนหนึ่งเขาติดมีตติ้งอยู่ถึงบ่ายสองครับ
อ๋อโอเค
เดี๋ยว
อันนี้
เขาจะตามมาครับ
ได้ครับมีติ้งเขาเป็น weekly หรือเปล่าหรือว่ายังไงเหรอ
อ๋อคือ ไม่ครับคืออาจารย์เขาว่างแค่เวลานี้ครับ
โอเค
เขาก็เลยครับผม
ก็เดี๋ยวสัปดาห์ต่อไปอาจจะต้องลองถามน้องเขาแหละว่านัดเวลาอื่นกับอาจารย์ได้ไหมเพราะว่านี่เป็นเวลาเรียนเนาะถ้าไม่ได้จริงๆก็เดี๋ยวจะอัดวิดีโอแล้วโพสต์แล้วกันแต่ว่าผมไม่ค่อยแนะนำเท่าไหร่เพราะว่าไม่งั้นเนี่ยถ้ามีคำถามอะไรมันถามสดไม่ได้มันก็จะเป็นข้อเสียนิดหน่อยอันนี้คือเห็นวิดีโอผมด้วยครับผมในนี้มันมืดตื่นเลย
เห็นครับ
อ๋อเห็นใช่ไหม Microsoft Teams สนุกอีกแล้วเห็นจอด้วยใช่ไหมครับ
เห็นครับ
โอเคนี่น่าจะครบแล้วเนาะเดี๋ยวเริ่มสอนเลยดีกว่า All right, so let's begin the class. One quick thing, I actually have my desktop opening with Microsoft Teams. And if you have any questions, feel free to put it in the chat. So I'm gonna take a look at the chat on Microsoft Teams. So if you have any question and you don't want to turn on the microphone, you can ask it through the chat. All right. So first of all, let me welcome everyone to the class, right? This is the Comar class that I'm teaching here at Vistech for the first time. So before we begin, let me actually, for this lecture, let me kind of brief over what is the computer architecture and why should we care, right? Anyone here heard about this terminology before, so I guess let me translate the question in Thai just to make sure everyone got it right. Is น้องๆเคยได้ยินเกี่ยวกับสถาปัตยกรรมคอมพิวเตอร์หรือเปล่าครับหรือว่ามันทำอะไรมีใครยกมือตอบสัก3-4 คน
ก็เป็นตัวท่านเป็นตัวท่านการทำงานของระบบคอมพิวเตอร์ครับ
มันเหมือนคือตามที่น้องวรรณพงษ์ใช่ไหมครับ
ครับผม
Okay, so let's do a quick show of hand here. One thing I can do is for Q&A, I can do the answer part both in English and Thai. And I hope that would basically help clarify things without actually breaking the assumption that we're going to teach in English, right? So let me do that, right? So you are basically suggesting that it's about like the system that govern how computer works, right? Which it is actually yes, and also it expand a little bit more beyond that, which is basically how you would design the hardware, right? ก็คือเกี่ยวกับการสร้างฮาร์ดแวร์นี่แหละครับ แล้วก็มันมีน้องๆคนไหนแบบอยากซื้อคอมใหม่ไหมแล้วก็แบบรู้สึกว่าเฮ้ยสาเหตุที่เราต้องซื้อคอมใหม่คืออะไร
It's not fast enough.
Yeah, it's not fast enough, right? So whenever you upgrade your computer, right, there are mainly the most important thing is whatever program you're running is not fast enough to run the program. So what's the most common thing that would drive my own demand of new computer? I cannot play the game that I just bought, right? So let's say I buy like Cyberpunk, which instant regret if you buy it on the launch day, but then you might run into the case that my GPU is not good enough, right? How many of you run into that? Like you buy a new game, you want to play it and enjoy it, and it turns out you cannot really enjoy the graphics because the GPU is not fast enough. How many times that happens to you? มีใครต้องเคยอัปเกรดเครื่องว่าการ์ดจอเร็วไม่พอครับยกมือหน่อยยกมือ
Right, 5 time.
Yeah, many people here, right? So especially for those gamers, including myself, we do that a lot, right? So let me tell you a story. The reason why I originally got into this area was I play games. I play a lot of games, right? And then I kind of want to figure out, okay, how does the computer actually make this thing? Like, how do you make a GPU? And then I kind of like start diving into that. And my thesis, if you are curious, if you check it out, basically it's about how to build GPU, right? How to make a GPU faster. I did transition into more like a high performance computing. So for those of you who, well, you're all at Wistech, I think you had the, okay, there's a question about the presentation. So if you're on the class website, I just upload the slides. So you can go to modules and you see the lecture. If it doesn't show up, let me know. I can make sure, I'm gonna make sure it's uploaded. But I think it does. So let me double check here. Yeah, it's not published. Okay, it should be up now. Sorry about that. I forgot to publish the module name, so it actually blocked you from seeing the lecture. But it should be up. All right, so that's kind of like a gist of like, why do we want to buy a new piece of hardware? So our field, computer architecture, is about how to build one, right? How to build the hardware to satisfy the customer, to satisfy the user. Right, so let me kind of transition into the content of this class, right? Before we begin, today we'll talk about what is this class about? Why do you why should you care? And after we are done through all the lectures, maybe you're like, oh, okay, it's just one of the class that I maybe enjoy or not enjoy. Some of you might want to got into the topic a little bit more. Your expectation, we'll talk about it today, and what do I expect from you? And a little bit notice, actually no homework zero. I decide not to do that. Nothing is due next Thursday, guys. My bad. Nothing is due next Thursday. The homework zero is basically like, it's kind of like an exercise on how to use C. So if you are familiar with C, you can skip it. There's no points for that. If you want to kind of do a refresher course on how to use Linux and C, check it out and see if you are comfortable with those kind of questions. Because if you don't, you need to catch up really quickly on how to use C, because our lab would be kind of heavily based on that. This is the graduate level class, so I'm gonna force you to read a few papers. In fact, there'll be 6 papers. Basically, you have to read in total 6 papers. It'll be based on theme, based on each of the week. So there'll be the first 3 weeks on kind of like the high-level overview and direction of architecture from the past, right? So basically, you look at the past and see how it's been progressing. So you can pick one paper and kind of review that. And then we'll start to read the paper on the core architecture, how the CPU works, followed by the main memory and caches and things like that. Basically, everything, when you combine it, it builds into like one single piece of hardware that you can run, which we call computer, right? These reviews are from the recommended readings that I'm gonna post. Basically, right now there's a list for the paper readings that I recommend. From your review, you pick one for each of the 2 weeks or 3 weeks, depending on the due date, and pick that one paper and review them. The papers I listed, most of them are papers that focus on the topics that we are talking about for each of the week. Some of them are more, some of them are older, but they are seminal paper that builds into the real products. Some of them are newer paper that are still topics that are under debate on how to design certain things. If you have any questions, again, feel free to turn on your microphone and ask me, or raise your hand, or just type it on the chat. But again, I'm basically monitoring the chat. So let me translate that in Thai quickly. น้องๆถ้ามีคำถามอะไรก็พิมพ์ใส่แชทได้เลยนะครับ หรือว่ายกมือ หรือว่าถ้าให้ผมไปเร็วขึ้นช้าลงพูดไม่รู้เรื่องอะไรยกมือก่อนเลย เพราะว่ามันเป็นออนไลน์เนาะผมไม่สามารถเนี่ยทุกคนไม่มีใครเปิดวิดีโอซึ่งไม่เป็นไรแต่ว่าผมจะไม่สามารถตอบได้เลยว่าน้องตามทันหรือเปล่าเพราะฉะนั้นถ้าเริ่มตามไม่ทันช่วยเปิดไมค์บอกเลยครับอาจารย์ครับเร็วไปครับช้าหน่อยหรือแบบอาจารย์ครับสไลด์นี้ไม่เข้าใจใช้ภาษาไทยเลยก็ได้คือเอาไงก็ได้ให้เราเข้าใจเนาะแต่เลคเชอร์เดี๋ยวขอเป็นภาษาอังกฤษเพราะว่าเราจะได้ฝึกภาษาอังกฤษไปด้วย So yeah, so if you want the slides, you go to the class website. So once you're on the class website, please go to modules. The class website is from the email we sent earlier to all of you. And then go to modules, and then from that, the PDF should be available right there. All right, so now that we've been through the really high level of expectation and high level of this particular lecture, let me talk about a little bit about myself, like who I am. Yes, thank you so much. So that's the class website. I think there's a sign up link as well. So let me put the sign up link on the chat, so you can just basically click on the link and you should be able to navigate to the website. So right here. So it's on the chat now. Click on that link. You will basically sign yourself up to the website. Who am I? My name is Rashada. I'm an assistant professor at TGGS. I got my PhD from Carnegie Mellon under my professor, my advisor, Ona Mutlu. He's one of the most prominent computer architects in the world. He actually has the most number of papers published amongst everyone else right now, I think. We work in computer architecture. I look into GPU, I look into OS, I look into how to design virtual memory for new type of systems like a GPU, or what if you have multiple GPUs or a CPU, GPU heterogeneous systems, right? I have interned at AMD Research. We did have one patent and one paper. That's actually my first paper in 2011 to ISCA. I'll talk a little bit about these conferences, but I'm sure you all are aware about these like top conferences based on your field, right? So I interned at AMD Research. I interned at NVIDIA Research before, as well as Intel Labs. The work at Intel Lab is more on the storage system side. And then before I graduated, I spent a year and a half as an intern at VMware Research. We did have 1, 2, 3, I think 4 papers out of that. 3 of which I was the first author, and 1 of which the collaborative works with my friends at University of Pittsburgh. I have actually put Kim. Anyone know about CS ranking? Okay, for those of you who know, if you filter just in Asia and ComArt, we are at number 11 right now. So CS ranking, if you don't know it, it only counts paper that get published at the top venue in the world. The reason why I really want to push this field in Thailand, to be honest, is to actually make sure that most people are more aware of what you can do, given the power of the hardware, right? Give me 1 second. สวัสดีครับครับมองไปข้างบนได้เลยครับบนกำแพงครับครับขอบคุณมากครับ All right, sorry, so many packages deliver around 1 to 2 o'clock. Sorry about that, guys. So I have my personal website here on github.io, and you can reach me through email at my email right here. One more thing about office hours. So this is upon request, so make sure you communicate with me. And basically let me know if you have anything that you want to make sure I'm aware, or if you want to catch up on certain topics. If you're looking at a PDF, I'm going to skip a few more slides. So the goal of this course is, this is the most important goal. I believe everyone here used a computer before. I believe everyone here is a programmer. You use computer to build things, right? So the course will teach you how does the tools that you are basically working on, how it works. How does computer works? After you finish, with the class, you should understand key techniques in computer architecture and understand different trade-offs in hardware design, right? Why is that good? Why is it actually important? If you know this trade-off, first of all, you can be a better programmer if you know, for example, how does caching works. That allows you to write code that whenever you have to access the main memory, instead of spending about 50 to 100 to 200 cycles, you can write a code that are cache friendly, and it only spends 3 to 4 cycles to access the data. That's about 10x speed up, right? Somehow your program is about 10 times faster, just knowing how the hardware works. It also allows you to think out of the box. So this is one of the things that I want to communicate to basically programmer as a whole, right? A lot of people assume that everything you do has to be dependent on the hardware you are running, which is true, But also think of it this way, you can change the hardware as well. Anyone here know about the tensor processing unit or TPU? Anyone heard about that before? So many people here might know about this thing called TPU, right? What it does is it actually is a piece of hardware. It's a core. It is a compute units that allow you to perform tensor processing. Tensor processing is used in what? Can someone tell me what do you use tensor processing for?
Deep learning.
Deep learning, right? So we use TPU to actually improve the throughput of your deep learning workload. Now your model is going to be a lot more accurate because you can actually, given the same amount of time, you can process more data, right? So think out of the box. In the worst case, you can figure out, should I buy this computer or should I buy another computer? Which one is better in terms of the cost benefit? So that's the worst case. Let's say you own your own startup company, and you talk to the sales team from 3 different companies that want to sell you a server. If you know how computer works, you can pick a server that gives you the most performance per dollars, which means that you spend the same amount of money, but you get the most out of your the things you want to run, right? Okay, so what do I expect from you? This is going to be a course that can be tough in some area. I am open to feedback, so if certain things are too hard, let me know. But I want you to work really hard, right? But this is a given. You are at one of the top school in Thailand, so I expect you to work hard. I kind of expect you to have basic system or hardware background, but don't have to know everything here. But you should know, whenever I said assembly, you should know what it is. I'm not asking you to actually write code in assembly, but you should know what is an assembly. You'll go through that together. I'm not going to require you to know basic Verilog, but knowing that is good. If you know basic Verilog, that helps. I demand you to know basic logic gates. How does AND work? How does OR work? What would happen if I do A and B or A or B? So you need to know that. I want you to have some basic system knowledge. What is an OS? What does the OS do? I want you to know enough that you can ask me questions that are related to these topics. I don't mind expanding on what they are, but I need to make sure you can ask questions. I want you to make sure you're okay with C and Linux. This would be where the lab is going. We'll use C and we'll use Linux. We are not going to ask you to build chips in Verilog. That's a little bit too much of an assumption. So I'm going to ask you to build a simulator. We will simulate a real chip in C language. I'm going to give you skeleton code, and I'm going to ask you to implement a fully, well, not fully functional, but a limited version of MIPS R4000. MIPS R4000 is one of the assembly language. It's one of the ISA used in this thing called PlayStation and PlayStation 2. Well, they didn't use the R4000, but they used the newer version of that. But it's actually based on MIPS architecture, right? So these are real real ship. I guess real ISA. You're not building a real ship, but you're building a simulator for that ship. I want you to attend lecture. If you have conflicts, I'm gonna post a video to make sure that you can watch what we cover basically. I want you to do all the required work. Sometimes it requires hard work. There are certain bugs that are going to be more common on your second lab, to be honest. And then on your third lab, you might run into a different set of bugs. So I want you to kind of think through that and let me know if you have questions. So that's come to the next bullet point. Ask questions, participate in discussion, which has been awesome so far. Whenever stop and ask you something, many of you raise your hand. Awesome. Do paper reviews and do not procrastinate, right? And the other thing is I do not tolerate plagiarism of any kind. So if you copy your friend's work, you both get an F. I'm gonna check. Trust me, I'm gonna check. So if I catch this is serious, and you are doing a graduate level, once you are done with the class, once you are done with the degree, you're gonna be one of the leaders like in the country to do certain things, right? I think this is an important thing that we have to teach everyone, including the older generation, right? You've seen old people copy things from someone else without quotation, and that's wrong. It's just plain wrong. I'm going to apply this policy in class to make sure that you do not plagiarize, right? I'm going to skip the slide about the class website. If you haven't signed up, go there right now. And I changed the breakdown. So just go with the syllabus. Don't stick with the slide here. So I'm going to change it to this. 20% assignment and 20% paper review. There'll be in total 20% for the exam. So these are basically your labs. Labs 1 to 3. These are paper review 1 to 6. You will have one project, right? Again, wrong number here. I'm sorry, guys. I decided to change it at the end. 20% for assignment, 20% for the paper review. The reason why I do this is when I put 30% on the lab, if you screwed up one lab, that's 10% of your grades. A little bit too much. Paper review, at least you guarantee if you do it well enough, which is not a big hurdle, you're gonna get full credit, right? So this particular breakdown is designed for me to make sure I can make the midterm harder, I can make the final harder without screwing up your grade. This is to make sure your grade stays pretty relatively okay, right? And don't worry, I'm gonna curve everything. Oh, you don't see the slides? Okay, let me stop present. Is that a problem? Anyone here see the grading breakdown slide?
I can see.
Okay, you're also shown as unknown user. So maybe can you disconnect and connect again and see if you can still see the slides? All right, I'm gonna give you some time to disconnect and connect again. In the meantime, มีคำถามอะไรไหมครับ
I have a question about your involvement with the. Maybe it's a long answer. Maybe we can ask
Yeah,
later.
go ahead. That's fine. Yeah.
So I heard in long time ago that those CPU companies such as Intel, etc., like, they try to hide the future technology because the marketing team don't want to sell it, just to make the price go higher. As in they have a lot of technology, but they just sell the bad one to get the most money out of it. Do you see something like that, or do you?
Oh, okay. So it's yes and no. So the way chip manufacturing works is imagine you have a big factory. By the way, give me 1 second. My cat is eating my wife's food, so give me 1 minute. All right, sorry. I It's need to take my cat away from food. I mean human food. No. Okay, so this is about the yield. I'm not sure if you heard the term yield before. What happened is when you want to fabricate a chip, let's say I want to pump out the Intel i9 processor of this generation, right? What would happen is I want i9 and then I go into the factory. It's like I produce a bunch of i9 chips. The problem is these factories are not perfect. Sometimes you cannot clock it that fast. So what happened is once the results come back, so let's say I produce 20 chips, right, that I want them to be all i9. What would happen is they're going to disable certain components from the worst one, like the one that you cannot clock it too fast, and sell it as an i5 or i3 processor. I'm going to disable some of the core because they don't work. It's the yield that comes from the factory itself. So they produce a bulk of that, and they're gonna categorize. Okay, this one is awesome. You can sell the full-blown design, and it would work as the specification for i9. Then you're gonna sell it as an i9 processor. This one only go up to the i7 specification. So I'm gonna just go with that. This one, i7 is fine, and you can overclock it, right? Anyone remember that some chips can be overclocked and some chips cannot? So if you can actually overclock, it likely suggests that when they test the chip, they know, right? So from the marketing perspective, they know that, let's say I have the customer buying 100 i9 chip last quarter. How many do you expect to sell this quarter? It will be based on how many you've sold, right? So if you somehow have too many i9 on the factory, what would happen? They're gonna lose money, right? Because I have the i9 chip sitting around, too many of those. So I'm gonna address that question afterward, after I tell the story. So basically, they're gonna categorize the chip and disable certain components that either doesn't work or doesn't work fully, so that you can still sell that as i3 or i5. Are they bad chips? No, they are perfectly fine as an i3 or i5 processor. So does it answer your question? อันนี้เห็นภาพขึ้นไหมครับ
เห็นภาพครับและอีก
โอเค
คำถามอีกอย่างหนึ่งครับว่าตอนนี้เขาขาย i11 อะไรเงี้ยครับเขามี i18 อยู่ในโรงงานแล้วหรือยังอะไรประมาณนี้
อ๋อ คืออันนี้ผมไม่ได้ไปอินเทอร์ที่ Intel มาสักพักแล้วแหละแล้วตอนที่ไปอินเทอร์ก็อยู่ที่ Intel Lab อ่ะมันจะไม่ได้คุยกับ Product Team เท่าไหร่แต่เท่าที่ผมเข้าใจเนาะคือเอาภาษาไทยแล้วกัน เท่าที่ผมเข้าใจเนี่ยก็คืออย่าง Intel ตอนนี้มันมีปัญหาเรื่อง yield ก็คือมันผลิตชิปแล้วเจ๊งเยอะ แล้วมันกำลังแก้อยู่คือมันกำลังพยายามแก้ที่โรงงานอยู่ว่าแบบเนี่ยจะทำยังไงเพราะว่า AMD และเพื่อนๆเนี่ยมันยิวดีกว่าเราตอนนี้เหมือนว่าแก้เกือบสำเร็จแล้วก็สามารถสเกลเป็นแบบ7 หรือ 9 นาโนมิเตอร์เนี่ยพอได้แล้วเพราะฉะนั้นชิปรุ่นใหม่ๆของ Intel น่าจะกลับมาสู้เพื่อนๆได้ด้วยราคาที่เท่ากันใช้คำนี้แล้วกันเนาะนี่คือความเห็นผมAre we at the limit of transistor size? Okay, let me answer the first question first. What architecture do we use for the assembly for this class? We're going to use MIPS, and we might have some sample from x86. But most of the time, for the purpose of this class, we will learn how do we create one assembly language. So we will use a simple one so that you know the concepts. One of the one that we're going to use a lot is called MIPS. It's really simple. It's a lot easier to use than x86. So I think that's a perfect for a class material. It gives you enough background on how each of the component works and gives you enough, I guess, foundation to learn the next ISA. Are we at the limit of transistor size? Yes and no. How big is an electron? Let me ask you this. How big is an electron? So what gets stored in a transistor? So let me reverse the question a little bit. What gets stored in a transistor? So in a computer logic gate, right? We use a bunch of transistors together to trap electron, so that we can measure the voltage. We read, how do we represent data in programming? It's in binary, right? Ones and zero. So the way the computer actually read data is either high voltage or low voltage. So let me ask you this question. Let's say my transistor is so small that I can only trap 5 electrons, maximum 5 electrons. How many electrons in the cell am I going to be able to categorize as a high voltage? If I have 4 electrons or 5 electrons, I guess, right? And if you have 2 to 1 or no electrons, that's low voltage. So you can see the boundary of errors that can happen goes up. The errors go up as the transistor size goes down. Can we reduce the transistor size? Yes. Is that kind of like erroneous-ish? Yes. So a lot of the topics in architecture these days, I think since about 2013 to 14 onward, it's all about, there's also a new area on how to correct errors, right? How do we correct errors that happen in your logic? Somehow suddenly your bit flipped from 1 to 0 or 0 to 1. How do we actually detect and flip it back so that we don't have the erroneous cell or erroneous data storage? So hopefully that answered the question, are we at the limit of transistor size? Yes and no. It's an awkward answer, but that's the truth. We actually at the end of Dennard scaling, which Dennard scaling is essentially kind of dictates how small a memory can be, right? And we are running into this thing called memory wall. There are new designs that address the memory wall problem. So the way architecture work kind of shift a little bit, right? Anyone heard about this Intel Optane thing? So Intel Optane, for example, is a new technology that support a new type of memory, right? That would allow, hopefully, in theory, right? You can go up to terabytes of memory. It's not DRAM anymore. It's a little bit slower than DRAM, but it's actually have large capacity, right? And who wouldn't want that, right? So basically, as technology progress, you're gonna kind of architect new things. Right. So let me continue with the class material. This is one thing I love to do. I go sidetrack all the time. If you enjoy new topics or things, just turn on the microphone, raise your hand, ask questions. These are totally fine. If it's already a part of the material, I'll tell you, oh, okay, wait until lecture X when we're gonna discuss those issues, but here's how it actually works. So these assignments and breakdown, the review would tell you the willingness, right, to learn new idea. Assignment and project would tell how you create something that new, you haven't learned that before, from what we cover, right? And the exam kind of determine overall, like whether you know the class material or not. And here's the things about paper review. Again, you're gonna do 6 paper review. 18%, so multiply everything by 2, right? It's 3% each, 18% in total, 18% in total. I don't do sloppy review, and I'm gonna explain later what it means, but don't just give me a summary of the paper and that's it, right? Make sure the review are at least good. You can submit any additional review. I'm gonna create a submission at an extra for that. And anything afterward is for extra credit at 0.25% your total grade per review. Right? So we have roughly 15 weeks you can imagine that there are 9 total that you can do, which contribute to about 2.5%. How much is that? It's about 25% of your exam, of one of the exam. So there's quite a bit. 2% class participation. So attend lectures, ask me things you do not understand, discuss paper you read in class. I might, if we have time, I might pick some of you to present the paper that you like. It will be more of a discussion rather than actual like, hey, you present. But basically, I'm gonna say, hey, how do you feel about the paper? I'm gonna randomly pick amongst all of you, and I'm gonna ask, so what paper did you review? What do you like about the paper? This will be roughly 10 minutes. I'm gonna, whenever I ask you, you're gonna lead the discussion, and you can ask your friends, basically hand it off to your friends so that you don't have to do the bulk of the discussion, but you can hand it off to your friend and say, okay, what else, anyone else to think about the paper? Anyone else read the paper? Or did you read the other paper? I want to hear more about it and things like that. All right, so now let's go into how to critique papers. Right? This is one of the most important things I'm gonna have to tell you. Every single paper has a flaw. Every single paper has a flaw. Some of them are easy to find. Sometimes the author said, this is the part that we did not do because we don't have time. And that's like another separate huge topic that actually works becoming its own paper, right? So that can be the easy to find flaws. Some of them are harder to find. Some of them require certain assumption to break the paper. Your paper review should include these things. It's a summary of the paper, pros and cons. The pros are easy. The pros are basically the author would tell you on the paper. The disadvantages is a little bit more tough, right? So I want you to integrate what you know so far, because one of the beauty of this class is you are all coming from different research area, right? None of you are mainly looking into architecture. So I want to see, okay, what if I assume that you're from, say, network or machine learning or image processing background? If you read the paper, can you find flaws that actually, if you run the workload you're having right now, it would break the design, right? And what can you do to improve the idea further? I don't want the part about how do you improve the paper, English. I want you to focus on the idea. And I will read all your reviews and I'll look at the effort you put into the review. I'll try my best to give feedback, but because there are about 15 to 20 of you, reading 20 reviews in 3 weeks can be a lot. So if it's good already, I might just say, hey, this is awesome, and here's how you can improve it even further. So I'm gonna try to see how I can have a feedback to improve your own review, right? Reading this paper will give you background knowledge, idea for your projects, and also improve your technical writing skill, right? These are all important. And one more hidden bullet point is, I'm not sure if you are aware that once you graduate, let's say you finish with your PhD degree, sometimes you are actually asked to review a paper. For example, I think I did about like 40 reviews a year, right? These are papers that get submitted to different conferences or journal that get sent to me, and I have to write the review for those. I have to actually decide if I want to accept the paper or reject the paper or do minor revision or major revision, right? So you need to be able to write these reviews. These are good practice for you going forward. Please don't plagiarize other articles. If you want to quote something from the paper, put a quotation in and say where it's coming from. I don't mind that happening. I just need to know it's from the paper, it's not your own word. All right. The assignment, you can have a few assignments. This forces you to apply concept we learn in class, and generally you're going to implement a part of a simulator that simulate real hardware. Initially, you're going to give skeleton code, and you're gonna implement some basic features so that your simulator can run MIPS assembly. It's not that hard. To be honest, assignment 1 is a huge if, else, and switch case. It's actually as simple as that. It's a huge if, else, and switch case to make sure when you have the binary coming in, you can process the instruction. Then we'll build from that. We'll build from assignment 1 into assignment 2. Your solution for assignment 1 will be used as a starter code for assignment 2. So make sure you finish assignment 1, otherwise your lack of work are going to cascade into second assignment. Assignment 3, I'm going to give you a new skeleton code so you don't have to start from assignments 2 code. And then you finish that and going into the class project. So everyone is expected to work on one final project. This is a big chunk of your grade. My expectation is it should be a 2-month worth of project at minimum. And it should be related to the material we learn in this class. You need to provide your own contribution one way or another. So please check me on some ideas, especially if you have some projects already ongoing with your advisor. I can try to figure out, okay, what project should you do to make sure that your effort for this class is not like go in vain and you don't do it anything afterward, right? So if you want to kind of integrate to your main project, let me know. How do you get ideas for your project, right? First of all, think about what's missing from our assignment. So one of the totally valid project is once you're done with assignment 3, you are going to realize that our simulator still assume a lot of things. It doesn't really simulate every single thing that we learn. So you can say, hey, I want to extend the simulator so that it actually take into account of, say, DRAM, right? So you can definitely do that, and I will welcome that. You can read paper from top tier venues. This is where I'm gonna expand a little bit on top tier venues in architecture. So how many of you are in, let's say, computer network? All right, how many of you are working with Ajahn Buck right now? Or Ajahn E or Ajahn Ek? Anyone? Or are you still deciding who would be your advisor? Okay, so Palakon. Okay, so for those of you who work with Ajahn Ek, what's your top venue for image processing? Can you tell me?
For me, I try to actually not do. I'm not doing the image processing. I do the radar signal processing.
Oh, signal processing. Okay.
But try to apply the machine learning on it.
Okay, so if you look into machine learning on the signal processing part, what would be your dream venue? Like, what would be your dream conference or dream journal that you want to submit?
Maybe right now sensor journal.
Yeah, sensor journal. That's awesome, right? For those of you, Panutev, so what topic are you working on?
I'm working on NLP field.
All right, so let me ask you this. What if you have a NIPS paper?
Sorry?
NIPS, NIPS, Neuro IPS. So Neuro IPS is like the top conference in machine learning, right? These venues, and if you work with Ajahn Buck, you might have seen things like NSDI and SIGCOM, right? So if you're familiar with SIGCOM, is one of the top venues. Basically, it's a work in this area that the best work go to, right? So if you work in computer architecture, there are 4 venues that is like the dream venue for students and PhD, even at CMU, Stanford, Berkeley, MIT, they all want to go there. It's ISCA, that's Micro, ASFLOS, and HPCA, right? This is like the absolute best conference for architecture papers. you can get ideas from reading some of this paper. You can say, hey, I read the paper and it sounds interesting. How do I implement this? How do I imitate what they did here? Let's say you want to do that for a project. You want to set up what they did. That's totally okay, right? That's totally okay. So if you got idea from this venue, check back with me so I can kind of like give you some more advice on how would you do the project based on this paper, right? And by the way, thank you so much so far for responding to me. This is awesome. Again, I really appreciate it. This is much better than a silent class where I teach and no one responds, right? You can check out the class website. If I have random idea, I'll put it there. I'll try to make sure the ideas can be finished in 2 months. You can also contact me, all right? You can talk to people who have taken this class before at TTGS. So if you want to talk to students who took this class before, let me know. I can give their contact to you to see if they have any ideas that would work or any advice for the project, right? So we're gonna have project checkpoint early September. We're gonna do a Q&A for the proposal. Right, Q&A for the proposal, and then late September we're gonna start to look into proposal. Mid-October I'm gonna have a checkpoint and to make sure that you did something, right? If you haven't done anything but your project is perfectly fine to be starting after mid-October and finish by December, that's okay too. I want to make sure you have a plan. This is basically to make sure you have a plan. Let me write it here. Make sure you have a plan. Because to be honest, whenever I have a class project, I do it the last 3 weeks of class. It happens to all of us. I just want to make sure you have a plan. Last week of class, you have presentation and the report. We will find a time, sometime, right? You are going to have 5 late days total. 5 late days total that you can use for assignments, projects, everything except for these 2 items, because this will be the absolute last day I can have. Any later than this, I will not have time to grade. So I'll make sure that I give you as much time as possible, right? The key here is learning. The key here is not to penalize you, to make sure you learn. This checkpoint help you prepare for the final report. And for the report, I'll enforce that you have to send it has to be written in LaTeX. It should be a PDF generated from LaTeX. Don't send me a Microsoft Word document. Do it as best you can. It's a practice for you to write your master or PhD thesis. It's a good way to practice your writing. Feel free to contact me on writing resources or examples of paper that I think I've written well, right? How many of you here read papers and you love how the paper explain things? น้องๆมีใครเคยอ่านเปเปอร์แล้วรู้สึกว่าเฮ้ยเปเปอร์นี้มันเขียนแบบเข้าใจอะไรยากๆแต่มันเขียนให้เราเข้าใจง่ายมั้งครับแบบไม่ใช่คิดละเคยไหมฮะ
ครับผม
ก็คือมันเป็นการฝึกสกิลเนาะมันเป็นสกิลหนึ่งที่จริงๆอันเนี้ย advisor ผมเขาพูดว่าเราต้องมีเลยก็คือเวลาเราเขียนเปเปอร์เราควรต้องเขียนให้คนอ่านที่ไม่ใช่คนที่ใช้ภาษาอังกฤษภาษาหลักเข้าใจเราได้ไม่ใช่แค่เราเขียนให้คนอังกฤษอ่านคนอเมริกันอ่านเราต้องเขียนให้คนที่อยู่จีนญี่ปุ่นเกาหลีอินเดียที่เขาไม่ได้แบบอินเดียใช้ภาษาอังกฤษภาษาหลักเนาะขอโทษทีสมมุติจีนญี่ปุ่นเกาหลีเนี่ยฮ่องกงไต้หวันคนพวกเนี้ยมีอีกมากที่เขาอยากจะอ่านแล้วเข้าใจเปเปอร์เราเพราะฉะนั้นการฝึกในการเขียนเปเปอร์เนี่ยจริงๆสำคัญมากเพราะว่าเราจะสามารถบอกคนอ่านได้ว่าไอเดียหลักของเราคืออะไรสิ่งที่เราทำ contribution หลักเมื่อเทียบกับเปเปอร์ก่อนหน้ามันคืออะไรพวกนี้จริงๆมันสำคัญมากเนาะมันเป็นส่วนมันเป็นจุดสำคัญใหญ่ๆอันหนึ่งเลยที่ทำให้เปเปอร์ impact ของเรามันขึ้นมาคือไอเดียสำคัญอยู่แล้วไอเดียคอนเทนต์มันสำคัญแน่ๆแหละแต่ถ้าเราเขียนเปเปอร์ได้ดีมันจะทำให้ impact สูงขึ้นไปอีกเนาะ ก็ไอ้ report พวกเนี้ยก็ถือว่าเป็นการฝึกหัดอย่างหนึ่ง Alright, any questions before we transition into what is computer architecture? รู้สึกใช้เวลาเยอะมากเลยกับการพูดเกริ่นว่าคลาสนี้มีฟอร์แมตอะไรบ้าง
มีคำถามครับเรื่อง textbook ประจำอันเนี้ยมันมีอยู่ที่ห้องสมุดหรือยังครับหรือว่า
เรื่อง textbook ใช่ไหมครับ จริงๆแล้วผมไม่ได้มี recommend อะไรหรอก จริงๆไม่ต้องใช้เลยก็ได้ ใช้สไลด์เราเนี่ยแหละ
อ๋อโอเคครับ
เดี๋ยวผมจะอธิบายทุกอย่างอันไหนไม่เคลียร์ก็ถามไปเรื่อยๆโอเคครับน้องที
โปรเจกต์อันนี้ individual ใช่ไหมครับ
โปรเจกต์อันนี้โอเคเป็นคำถามที่ดีมาก ถ้าอยากเป็นทีมให้บอกผม แต่ผมแค่จะบอกว่าถ้ามันเป็นทีมปั๊บเราต้องแบ่งให้ชัดเจนว่าใครทำอะไร เพราะว่าเดี๋ยวผมก็จะสัมภาษณ์น้องทีหลังว่าใครทำอะไร ตอนเราพรีเซนต์ก็ถ้าอยากทำโปรเจกต์เป็นทีมได้เลยผมไม่มีปัญหา up to 3แล้วกัน let's do up to 3 people per project. You can do individual projects, you can do 2-person's project, and you can do 3 people's project. Obviously, if you do 3 people's project, the work that I'm going to expect would be 3 times more than individual projects. เพื่อความแฟร์ของน้องที่ทำคนเดียว
Okay, thank you.
โอเคครับ มีคำถามอะไรเพิ่มไหมครับ ถ้าสมมุติเรียนไปแล้วรู้สึกว่ามันเยอะไปก็ช่วยฟีดแบ็กผมด้วยนะครับ ผมจะได้โทนดาวลงมา คือผมก็ไม่ได้ปีศาจเนาะคือถ้ามันเยอะไปให้บอกเนาะนิดนึง เพราะว่าผมก็เข้าใจว่าน้องๆหลายๆคนคือนอกจากจะมีโปรเจกต์ก็ต้องทำรีเสิร์ชแล้วก็เรียนคลาสอื่นด้วย แล้วก็จะขอ make sure ว่ามันไม่ได้แบบ overwhelming มาก โอเค งั้นเดี๋ยวขอ transition ไป topic ต่อไปเนาะ น่าจะใช้เวลาประมาณ40นาทีก่อนที่เราจะ break แล้วพอเรา break เราก็จะมา finalize กับ topic สุดท้าย alright so let's transition into what is computer architecture, right? So let me ask by anyone seen this before? Well, not this picture, but this building. Can someone tell me what is this? It's the Louvre. Thank you. Yes. This is in Paris. So I took a picture. This is one of the good sides about being in computer field, right? Because a lot of the venues that we go to for conference are all over the world. So when we go to present our work, we get to enjoy the city. So this is a conference in Paris. So I went there and I took a night stroll to the Louvre. Sadly, it's closed for sure. It's already like 6 p.m. In Paris around the time. So I took a picture. So if you think about it, right, this is one of the architecture masterpiece. Why is that the case? Anyone? So น้องพารากอนใช่ไหมครับ
พลากรครับ
พารากอนน้องเคยได้เข้าไปข้างในป่ะครับ หรือว่ายังไง มีใครเคยไปลูฟหรือเปล่าถามนิดนึง
ไม่เคยครับ
So this building is kind of interesting in a sense that this is the top of the museum. Actually, the museum is actually underground, right? So the way they built it is you go in through the front gate over here, right, to the left. This part, this is where you go in, right? And then you take the escalator down. And that's where they charge you money to go into the museum. And there are multiple wings around here. So if you go into the building, you see to the left and to the right, there are going to be different art pieces inside the building that you can kind of see from the windows, and it's all underground, right? So the way the architect built this building is they somehow built this pyramid thing that behaves like an entrance, and it actually does look really grand, right? It looks nice. So it does serve the purpose of making sure you can store a lot of these art pieces safely, right? Because it's underground, it's also pretty safe. It allows you to go in and enjoy the view. And it allows you to go in and kind of like go into different buildings based on the theme of the artwork, right? So this is the architecture masterpiece. Another was this. Any guess on what is this? It should be pretty obvious. It's a waterfall, right? It's a waterfall. This is a waterfall. It's actually called Cucumber Fall. It's in the Ohio State Park in Pennsylvania, about 2 hours from Pittsburgh, which is where CMU is located. So I went here pretty often with my friends. Whenever I have a friend coming from out of the state, right? This is one of the default place we're gonna take people to because not because of this waterfall, but there's another building nearby. What happened is, let's say you are rich, and I say I want to build a house on a waterfall, right? And I talk to an architect. I have money. I want to build a house on a waterfall so that I can enjoy it, right? And this is a real building. Anyone have seen this before? So this building is called the Falling Water. It's one of the UNESCO World Heritage Site built by one of the master architect called Frank Lloyd Wright. He is one of the architects that built many buildings in the United States around the time he's living, right? So that's the job of an architect. How do you build a house to make sure, right? I give the customer whatever they want, right? Whatever the user wants, right? So let me ask the same question. Then what about computer architect? We design computer, right? We design computer, but here's the deal. First of all, I need to fundamentally understand the circuits, how the circuit works, right? So that I can put things together. It's similar to how real life architects need to understand how building works. How does you put in different bars and the concrete to make sure it doesn't collapse, right? You'll be sad if your house collapses because of an architect is not doing his job, right? They need to work with engineer to make sure every structure holds. Similar to computer architecture, we work with circuit people to make sure that we have every single piece of circuit on the board correctly. You need to also fundamentally understand the software, right? Why is that the case? You need to know if I want to build a tensor processing unit, I need to know what is deep learning. How does it run? So I built the hardware that actually is fast, so fast when you run deep learning workload, right? You also want to build the machine that matches the user demand. Why is the last bullet point here important? Anyone here want to take a guess of why is this important?ทำไมผมต้องแคร์ว่า user จะใช้ hardware เราหรือเปล่า
Because if it doesn't match, then no one use it.
Yeah, because otherwise no one use it. Otherwise my company will go bankrupt, essentially, right? So I need to sell, right? I need to sell my chip. I need to sell my computer. So whatever I build need to match the demand, right? So let's go into the topic of how do I evaluate whether the design is good or not, right? What's the most important thing? What is the most important thing that you care about your computer? Beyond the part that it works. So obviously it has to work. But what is the next thing that you care about?
It can serve the job that we design.
It delivered the task, right? And also it should be fast. Performance, right? Performance. You want to make sure that you have a design that performs well. It should provide the functionality that whatever you need to run, right? And it should be cheap, right? Who wouldn't want a cheap, fast computer? Right? That would be like perfect. Cheap and fast and have functionality, have a proper usability. Anything else? Energy. How many of you have a mobile phone with a battery that lasts only like 5 hours? Especially if you play games on the phone. Can you raise your hand? Yeah, I do have one too. My phone only lasts like, I think 2 hours if I play games on it. So wouldn't it be better if your phone lasts 2 days instead of 2 hours, right? So that's another design aspect that you need to deliver. Energy efficiency, power efficiency, right? These are always one of the key goals in designing a good computer, right? In designing a good computer. Our job is to identify and achieve them. So these are the role of architect, which I adapt from Yale Pat's lecture note. Yale Pat is one of the prominent architects, computer architect, who was my advisor. So I guess he's my grand advisor. He's right now a professor at UT Austin. And he's one of the leading researchers. Back in the day, he was working on branch predictor, which go into the Intel chip. So he said, we need to be able to look backward. You should be able to look at the old code and understand design trade-off, pros and cons. Analyze previous design, not just old code anymore, old design. You need to be able to look back in time and see what went wrong and what is good, right? You want to be able to look forward, listen to dreamers. Listen to dreamers. What do I mean? I want to know the demand of new applications. This is one of the things I'm trying to do all the time, which is I talk to my friends in the other area so that I know what are the demands that are coming from people who work in the application field, right? So that I can keep pushing the state-of-the-art design. I push the new hardware to satisfy my user. I need to look up. I need to know the nature of the problem. Look up the software stack, right? Look up the compute stack. Fundamentally, this particular program requires certain algorithm. For example, it might demand graph algorithm. So I might want to build the hardware to make sure graph algorithm is fast. These particular, what is the most common thing in deep learning? Can someone tell me what is the most common operation in deep learning?
Multiplication.
Matrix multiply, right? So if I somehow know that, hey, the software do a ton of matrix multiply, then I can build the hardware to do just the matrix multiply, right? Which basically becomes the tensor processing unit, right? So if you know the nature of the problem, it allows you to build the hardware that actually make a lot of sense, and it deliver performance at cheap cost. Performance per dollars is so important to everyday user. You also need to look down, know the future technology, look at material science paper, look at circuits paper and say, oh, okay, this device look interesting. It's likely to become the next generation of computer. You want to understand the capability of the current technology and predict and enable future technology, right? So now that I talk about looking up and looking down, so let me talk a little bit more about compute stack. How many of you heard about this word, front end and back end developer? Front end and back end. We all seen that before, right? And if you work in this tech with any professor there, you probably realize that that's not the only thing in computer, right? You're like, what about image processing? We need to look at the driver. We need to look at how GPU render things, right? If you look in database or if you look at network, for example, you know there's a network stack. You know there's a system stack. If you work in deep learning, you know that sometimes you need to modify the system to make sure you get better and better throughput. Right? You need to work with a GPU, for example. There's a lot of things going on underneath, right? Which sadly, this is one of the main drawback of the computer industry in Thailand, that they only know front end, they only know back end, that they don't give a crap about the rest, which is big, right? Which is really big. In truth, the computing stack is something more like this. You have a problem. that problem get converted to the algorithm. Then the algorithm get put together into the program, right? That's kind of where the front end and back end stop, right? And then you deploy the program, done, yay. But in reality, when you finish writing a program, you need to compile and you need to run. You need to run in the runtime system, which involves driver code, network, database management system, I already said network, hard drive, storage system, file system, many components that go into this part of the compute stack, right? And then you have the ISA, which is basically your assembly code that translate to the microarchitecture. In this course, our computer architecture class will touch these 3 layers of the compute stack, from the runtime to the ISA to the microarchitecture. We will not talk about the logic and device and electrons, right? Because I'm not going to demand you to know physics or digital circuits. It's a little bit too much to ask. But whatever we design here, because of this compute stack, right? Because of this compute stack, if you modify something in here, it is going to affect the programmer, right? And if you think about it the other way, what we are is kind of like the link between gate and wires to the computer codes, right? So with this link, we introduce the power of abstraction. Because as a user, more abstraction leads to more productivity. Why? If you're a programmer, how many people enjoy writing code in Python versus C? Which one do you like more? Which one is easier to finish? So you like Python, right? Obviously, I do too. If I don't have to use C, I will use Python. So the power of abstraction give the Python the power for the programmer, right, to not having to know what happened to a lot of things when you run the code, right? You can just declare a new variable. You don't have to worry about the main memory, right? You don't have to. Anyone here use C before? Can you raise your hand? Anyone here seen this thing? Or I still have nightmare with this thing? All right, I see a lot of hands. Segmentation fault, right? Everyone's nightmare when you're using C and memory allocation. Python don't give you that. Java doesn't give you that. Java and Python have their own garbage collector, which by its own manage everything for you. Programmer doesn't have to be aware. I allocate the memory and garbage collector would take care of it. Yay, right? This is awesome. So this power of abstraction give programmer a lot of ability to keep pumping in great code, right? That do a lot of useful things, which is really awesome. The question is, then if I said this, why do I care? Why should I care about the system? Because ideally, as a programmer, I don't want to be able to know how the system works. I just want to program. And that's kind of like the deal behind things like serverless computing or a lot of this like new technology in system like microservices, right? And new technology in programming languages like Python, right? Or like even Rust and all these new languages that kind of get rid of common system bugs from your program. The problem? What if your code is slow and it does consume too much energy, right? And you say, hey, okay, code is slow. I don't have enough power supply. So let me switch to a new machine. Turns out it's even slower. So this is rare, but how many of you like switch to a new computer and it does run slower? Your program sometimes runs slower, right? If you work in, okay, one person raise your hand, thank you. If you does work in machine learning and you have to utilize the GPU, one of the more common thing is you upgrade the GPU. Sometimes you have to re-optimize everything. You have to re-optimize your code for the new GPU, right? So this can happen. Program produce incorrect results or seg fault, right? So if you know how computer works, you can kind of like know, okay, seg fault happened because of permission. It's an error because you're trying to access a location that you didn't own, right? Sometimes your code makes your computer hang. This happened a lot. How many of you have this happen? You run a program, 5 minutes later, it hangs. The entire computer hangs. Or you play a game and the game you're playing hangs your computer. I'm sure that happens to everyone when it comes to gaming. And you get sad because you haven't saved the progress yet, right? And you have to replay a lot of things, and you yell at the developers, right? So these things can happen, or even your code shuts down the computer by accident, right? Sometimes I have that happen to my test program. So I basically want to test how much can I squeeze out the GPU to the point it actually shut itself down. So it does happen. So knowing how computer really work can help in these scenarios because you know why does it hang, why does it shut down, and you can address the problem without guessing. You ended up having to guess, but guess a lot less. You know potentially this can happen, so you try to address each thing. Right. So let's look at some obvious real world example. We talked about this already. Matrix multiply, right? When you do block matrix multiply, it will improve the cache hit rate. So what application, the part we talked about already is, what application use a lot of matrix multiply? I think Nong Paragon already answered that before, but I might be wrong. Deep learning, right? So deep learning use a lot of matrix multiply. So what if let's say you can do multiply in parallel, matrix multiply in parallel, like on a GPU, right? So in fact, if you listen to there was one year where a group of scientists got the Turing Award. Anyone here know about what is Turing Award? So you know Alan Turing, right? The one of the like forefather of computer. The Turing Award is the award named after Alan Turing, and it's given to, it's like a Nobel Prize for computer scientists and computer engineer, right? There's one year where a team of scientists who worked and who kind of paved the way for machine learning, who as a group got the award, right? And the Turing Award lecture, inside the Turing Award lecture, they actually cite the importance of hardware advances because machine learning has been there for a long time. We just never have a computer fast enough to run machine learning so that it becomes useful. Here comes the GPU. Suddenly, somehow, maybe computer architect talks to machine learning guy and like, oh wait, it's the same exact thing that we run on graphic applications. So let's run ML on GPU. And the advances in hardware actually enabling the machine learning as you know it, right? Because it's really involved. That's why you need, many of you would need a powerful machine to run your deep learning workload. So GPU has been used in modern systems. So if you look at this, for example, this older GPU, RTX 2080 Ti. These days you have the 3080, which is faster. If I buy it, I'm gonna buy it to run these games, which I did play, right? But if you work in research, you also know that the GPU can be used in many tasks, like using CUDNN or NV graph to process data for graph application or a DNN workload, deep learning, TensorRT. All these things are possible because of the parallelism that the GPU provide, right? We will learn in this class, toward the end of this class, we will learn how the GPU works. So hopefully when you look into your friend deep learning workload, deep learning training workload, and also inference workload, you see where the performance gain is coming from, and hopefully you can kind of adjust the configuration. So hopefully get more throughput, right? NVIDIA these days also come up with like Titan X A100, where you can have the GPU being shared amongst many clients. And these are all possible because of their massive parallelism, the actual fundamental design behind the GPU. And with this real world example, anyone here tried running random program on a GPU without like running like PyTorch or TensorFlow? Okay, what do you feel? Is it hard to write one?
Yes.
Right? So it can be really hard to write one, and it also can be really hard to write a fast one. Why is that the case? The A100 GPU, which I think Vistec actually have one, it's a pretty really powerful machine, but you should know the hardware because the way it works is program that you're writing has to be embarrassingly parallel. You need to be able to do thousands and thousands, if not millions of things in parallel to make it fast. And these parallel operation also has to be the same exact operation, like matrix multiply. Matrix multiply is just multiply a bunch of data, and then add, right? So it's a lot of the same operation after another. Otherwise, the GPU would be crawling. It's gonna be super slow. It's gonna be actually by design. It's gonna be slower than running on your CPU. Right? So if you know the hardware, you will be less clueless and think that GPU is a solution to everything. No, it's not. It's a great solution for certain things and a really bad solution for other things. What are other examples? Anyone here heard about the meltdown on Spectre? It was an attack in 2018. These are bugs that happen in the CPU where you can attack a machine with a thread running, and you can peek into what is the data that the other programs are running. And this attack kind of spawned a lot of security research on hardware. Right? How do we protect the hardware? Another attack that happened is actually come from the lab I was in at CMU. My friend, his name is Yoongu Kim, was basically, he's one of the leading researcher in the group that worked in DRAM. We basically built a lot of new DRAM design. So we were testing DRAM, right? And it turns out, if you write certain patterns to DRAM, we found that you can flip the bit at some other location, which means that you can write a program that safely running in the OS. Linux wouldn't know this is an attacker, but somehow it flips someone else's data from 1 to 0, from 0 to 1. This attack is called roll hammer. And there's a lot of follow-up works into how we can utilize this to hack someone else's machine. There's already a use case for JVM, I think. And also, I think Google took a look at it, and Apple, the iPhone actually have to patch specifically for this particular bug. So in the paper that Yoongu Kim published, it actually contains like some ideas to like how to fix it. It does come with performance overhead, but at least you don't get attacked, right? What else can you do with hardware? Anyone here work on DNA sequencing? Anyone here coming from the joint program between like biology and bioinformatics here at all? Okay. Oh, okay, there's one person. Raise your hand. Nice. So if you work on DNA sequencing, you know that one of the main tasks is called sequence alignment, right? Basically, the main thing is it's almost like the string matching problem. So in computer science, string matching is you have a target and you have the pattern you want to match, and you want to figure out where does the pattern show up in your source string, right? So you want to make sure it match with some error because you can have mutation in your DNA. You can have insertion, deletion, or substitution. One letter pops up, one letter got deleted, one letter changed from A to G, some things like that, right? So if you know how the hardware work, you can actually do the sequence alignment all in DRAM without even involve the CPU. With minimum involvement from the CPU, to be honest. You kind of have to trigger this, and this will be run on the 3D stack DRAM. So this is a work that we just published in Micro 2020 this year. Wait, no, 2020 was last year. So this was published last year. Yeah, last year in Micro 2020. And our proposal is to use the logic layer within DRAM to perform the sequence alignment by simple arithmetic logic, right? Basically, we have to do string matching and dynamic programming. Basically, it's a hardware that's designed to do string matching and dynamic programming. And we are able to accelerate the workload about 100th of time faster than a software solution. So if you haven't bought it yet, so what are other reasons? Advance in hardware enable new technology like modern day machine learning, IoT. Design a hardware to be more power efficient, meet the latency goal and throughput goal. Right? If you want to build a self-driving car, you want to make sure you can detect objects without the car actually hitting that person. So you need to be able to provide these guarantee. You want to improve reliability. You want to make sure when the system goes down, the hardware goes down, you can still save certain computation that you're doing and communicate out through some other devices. It can enable cool graphic and video games, which I think we all enjoy, right? And also one last few reasons, there's a high demand. This might surprise you. There's a high demand for people who know computer architecture and computer system. Why is that the case? A lot of programmer has little knowledge on how computer actually works. So if you know that you can optimize your code, you can understand and analyze where is the performance bottleneck and scale the program so that you can handle more clients and workload. And you can further optimize the popular workload that you've been using so far, right? And scaling the program is kind of like related to this slide I'm going to show you. It's like so that our community stop launching web app that doesn't scale, that crash every time you have people signing up for things. You've seen this before, right? Anyone here raise your hand who remember this last year? How about this? And how about this? These are all preventable problems, right? Let me give you one particular example from this, actually from the system, right? The more prompt system. They claim that, hey, we tested and we can handle 20,000 transactions per second. 20,000 transactions per second. That's a really, 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 really low number. If you look at modern system that most company deploy, we are talking about hundreds of thousands to 1 million transaction per second. if you read OS paper, system paper, distributed system paper, and you somehow say, hey, your baseline is 20,000 per second, 20,000 transactions per second as a baseline, I'm 100% sure every single reviewer will say, how do you configure your baseline system? Because that's not realistic. It should be roughly maybe 1 million, right? So these are some of the things that are happening that I wish, right? If people, developers knows more about computer hardware, computer OS, basically the system software, we can together, right, reduce people's suffering where things go down, right? Things are going to go down. And I can predict in the future, this would happen more and more because there are going to be more users. We did a really good job, right? To be honest, as a user, I love that UI, I love that UX, to be honest. UX is whenever it doesn't go down, right? It's not too bad. But it doesn't scale. The thing is, it doesn't scale at all. So hopefully things we learn from this class would kind of contribute to all of you who graduate, right? And be aware of at least like how to test it. So to make sure that, hey, it doesn't scale, so don't launch it yet, right? All right, so that's hopefully motivate why you should care about things we're gonna learn in this course. So let's take a quick break because it's right in the middle of the lecture slot. So let's do a 10 minutes break. I'm gonna go get some more water and I'll be back at 2:35 for a Q&A. So if you want to ask question, I'm gonna come back at 2:35 and then we'll do a 5 minutes Q&A and we resume at 2:40. Is that okay? All right, so let's do a quick break and we'll resume at 2:40. โอเค กลับมาแล้วมีใครมีคำถามอะไรไหมครับ
อยากรู้ว่าตอนที่โปรแกรม arithmetic บน DRAM อะครับมันทำยังไงอะครับ
อ๋อโอเคคือจริงๆถ้า DRAM มันจะมีเทคโนโลยีใหม่ที่เขาเรียกว่า 3D stack DRAM นี่ไม่รู้น้องๆเคยได้ยินกันหรือเปล่า จริงๆมันใช้อยู่ใน GPU แล้วนะไอ้ GPU รุ่นใหม่ๆมันจะเอาเหมือนชิปของ DRAM ที่เราสมมุติเราซื้อ DRAM ใช่ไหมเห็นไอ้ชิปดำๆนี่หรอกใช่ไหมครับดำๆบน DRAM
ครับ
อันนั้นคือชิปที่ไว้เก็บ Data ไอ้ 3D stack DRAM เนี่ย คือมันเป็นเทคโนโลยีที่สามารถเอาชิปมาต่อกันปุ๊บโดยที่มันไม่โอเวอร์ฮีทคือมันจะทำให้เราสามารถโอเปเรตเป็น3 มิติได้ แล้วข้อดีของไอชิปแบบเนี้ยที่เป็น 3D stack DRAM นอกจากจะเพิ่มตัว bandwidth เพิ่ม capacity ได้ใช่ป่ะไอเลเยอร์ล่างสุดมันสามารถสร้างเป็น logic layer ได้ logic layer มันก็คือเป็น material ชนิดเดียวกับของ CPU เรา ซึ่งเราสามารถใส่ทรานซิสเตอร์เข้าไปได้ เพราะฉะนั้นตอนนี้มันจะมีarea เล็กๆ อันหนึ่งที่อยู่ใน architecture ที่แบบเขาเรียกว่า processing in memory processing in memory ก็คือเหมือนเราสร้างชิปตัวเล็กๆไว้ติดกับ memory เลย แล้วก็data ที่วิ่งมาจาก DRAM ยังไม่ทันออกมาจากชิปของยังไม่ทันออกมาจาก DRAM เลยนะ คือมันจะสามารถวิ่งผ่าน logic ตรงนี้ได้ แล้วก็ process ข้อมูลได้ เพราะฉะนั้นถ้าเป็น workload ที่เป็นแบบแค่บวกลบคูณหารอะไรพวกนี้เราสามารถเอามาทำบน DRAM ได้ แล้วทำไมเราถึงทำคือจริงๆCPU เรามันคล็อกมันเร็วกว่าอยู่แล้ว คือยังไงตัว performance บน CPU มันจะเร็วกว่ามากๆ แต่ข้อดีของการทำบน DRAM คืออย่างแรก เราไม่ต้องรอ data วิ่งจาก DRAM ไปที่ CPU data ที่วิ่งจาก DRAM ไป CPU ให้นึกภาพ mainboard เนี่ยในน้องไม่รู้น้องเคยน้องชื่อปฐมป่ะครับผมยังไม่
ครับปฐมพรครับ
ปฐมพรโอเคก็ผมเห็นชื่อภาษาอังกฤษผมไม่อยากแบบ murder ชื่อภาษาไทยผม
โอเค
อ่านคือถ้าน้องลองนึกภาพเมนบอร์ดที่เราซื้อใช่ไหมแล้ว CPU ก็แปะอยู่ที่หนึ่ง DRAM ก็จะเสียบอยู่กับช่องอีกจุดหนึ่งการที่ CPU มันจะได้ Data จาก DRAM ให้นึกภาพว่าอิเล็กตรอนมันต้องวิ่งจากตรงนั้นไอ้แท่งนั้นวิ่งเข้ามาจนถึง CPU ผ่านเมนบอร์ดไอ้ process เนี้ยมันใช้เวลา การที่เราเอา logic layer ไปแปะกับ DRAM เลยไอ้ตรง data transfer พวกนี้จะเร็วขึ้น และ bandwidth เยอะขึ้น คือ bandwidth internally ใน DRAM จริง bandwidth มันเยอะมากเลยนะ แต่ว่า bandwidth ของ DRAM กับ CPU ไอ้ช่อง bus ตัวเนี้ยมันถูกลิมิตด้วยจำนวนพินที่ mainboard มีให้เรา ไอ้ทองแดงไอ้สีทองเหลืองที่เราเห็นอันนั้นคือ1 พิน เพราะฉะนั้นถ้าเรานับนั่นคือสายไฟ1 เส้นที่ส่งอิเล็กตรอนได้ทีละ1 ตัวอันนั้นเป็นตัวจำกัดแบนด์วิดต์พอเราทำเอา logic layer ไปติดกับชิปได้เลยเนี่ยมันจะทำให้เราสามารถทำ computation แล้วก็ได้แบนด์วิดต์เยอะมาก
โอเคขอบคุณครับ
ครับ
พอ get idea ว่ามันน่าจะไม่เสีย latency เวลาข้ามมา CPU ใช่ไหม
ใช่ก็คือมันจะเสียเวลาในการทำ transfer data จาก DRAM ไปที่ CPU น้อยลงเยอะมากเพราะ CPU ตอนนี้มันอยู่ที่ DRAM แล้วไง
อ๋อแบบอีกคำถามสั้นๆได้ไหมครับ
ได้เลยครับได้
เวลาตอนที่อาจารย์ทำตรงนี้ครับตอนเขียน instruction set หรือตัว compiler มันคืออะไรครับ
เป็นคำถามที่ดีมากอันนี้จริงๆแล้วคืออย่างโปรเจกต์นั้นคือเราจะ assume ว่าเราจะไป extend ISA ถ้าสมมุติดันอยู่บน x86 เขาก็บอกว่าเนี่ยเราจะ assume ว่ามันจะไป extend มี instruction ใหม่ใน x86 ที่ถ้า call instruction เนี้ยมันจะโยนบล็อกของโค้ดที่เอาไว้รันไปที่ logic ใน DRAM แล้วก็จะไป trigger บอกพร้อมรันเท่านั้นเองคือมันเหมือน ISA คือไอตัว x86 architecture อะไรพวกนี้ไอ assembly อย่างเงี้ยมันให้คิดเหมือนมันเป็น interface ตัวหนึ่งที่เอาไว้คุยกับฮาร์ดแวร์เพราะฉะนั้นถ้าเราจะทำให้ฮาร์ดแวร์พวกนี้มันรันได้เราก็เหมือนเราไป add instruction ใหม่ได้ compiler ต้องทำยังไงอันนี้เรายังไม่ได้ไปถึงขั้นนั้นก็คือจริงๆแล้วเราสามารถเขียนเป็น instruction ใน assembly ได้ถ้าจะให้มัน compile code ออกมาด้วยเนี่ยมันมีพาร์ทที่มันต้อง involve ว่า compiler ต้องไปอ่านโค้ดก่อน pass คือเวลาเรา compile code เนาะสิ่งที่เกิดขึ้นก็คือ compiler มันจะไป process code เราอ่านทีละบรรทัด อย่างแรกที่มันจะทำก็คือพอมันอ่านทีละบรรทัดเสร็จมันจะทำสิ่งที่เรียกว่า tokenization tokenization ก็คือพยายามแยกโค้ดเราให้เป็นโทเค็นแต่ละโทเค็นอาจจะเป็นชื่อ variable x เครื่องหมายเท่ากับชื่อ variable y อีกโทเค็นหนึ่งก็คือเครื่องหมายบวกอีกโทเค็นหนึ่งก็คือ variable a b c d อะไรก็ว่าไปแล้วมันก็จะเอาโทเค็นพวกนี้มาแมทช์กันเป็นแบบ a บวกโทเค็นที่เป็น variable a มาบวกกับโทเค็นที่เป็น variable b อะไรอย่างนี้แล้วพอมันทำพาสนั้นเสร็จมันจะได้เป็นโปรแกรมในรูปของกราฟอะจริงๆแล้วมันก็คือเป็นกราฟชนิดนึงแล้วมันก็จะทำพาสอีก2-3 ทีเพื่อ optimize code ใช่ไหมปัญหาคือถ้าเราจะ convert อันนี้เป็น convert code อะไรก็ได้อะให้มันกลายเป็นฟังก์ชันที่เราจะไปรันบนฮาร์ดแวร์ชนิดใหม่พวกเนี้ยมันทำยากเพราะว่า compiler ต้อง detect ให้ได้ว่าฟังก์ชันเนี้ยมันคือโค้ดสำหรับฮาร์ดแวร์ตัวนี้วิธีที่เราส่วนมากเราจะใช้เป็นช็อตคัทกันก็คือมันจะมีหินมีน้องคนไหนเคยใช้ OpenMP ป่ะครับ
เคยอยู่ครับ
OpenMP วิธีการใช้ OpenMP คือไงเราใส่เครื่องหมายไอ้สี่เหลี่ยมอะ pound key ใช่ไหมก็ OMP อะไรก็ว่าไปนั่นนะครับอันนั้นน่ะเป็นหินให้ compiler บอกcompiler ครับโค้ดตรงเนี้ยเอาไปรันบนเป็นแบบ OpenMP ได้เลยครับผมเขียนมาให้แล้ววิธีทำก็คือเราสามารถใช้หินแบบนี้ได้เขาเรียกว่า pragma แล้วก็ใช้ได้เหมือนกัน
ขอบคุณครับ
ครับโอเคมีใครจะถามได้อีกไหมครับผมชอบออกทะเลเป็นเรื่องปกติเพราะฉะนั้นถ้าใครจะชวนออกทะเลผมก็พร้อมออกเสมอโอเคตอนนี้ก็ยังไม่มีใครออกทะเลกันเพราะงั้นเดี๋ยวเราจะขอสอนต่อแล้วกันเนาะเบรกกันหวังว่าจะได้พักรู้สึกผมพูดค่อนข้างเยอะถ้ามีคำถามอะไรเพิ่มเติมพิมพ์เข้ามาในแชทได้เลยนะครับผมก็ยังดูแชทต่อไปเรื่อยๆก็ถ้าผมไม่มิสอะไรถ้ามิสก็รบกวนยกมือด้วย แต่เดี๋ยวผมจะขอต่อท็อปิกต่อขอโทษปากกาไม่โดนผมจะขอสอนท็อปิกต่อไปก็คือแล้วคอมพิวเตอร์คืออะไรคอมพิวเตอร์คืออะไรถ้าเราไปเปิด dictionary ของอันนี้โค้ดมาจาก Oxford English Dictionary ก็คือคอมพิวเตอร์แปลว่า an electronic device for storing ผมต้องสอนภาษาอังกฤษนี่ sorry ครับขอโทษทุกคน so what's a computer if you open a dictionary it basically would say that it's an electronic device for storing and processing data typically in a binary form according to instruction given to this in a variable program seems like a long definition but it's a really 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 good definition why is that the case it's a machine, it's a device, right? It's a device that, let's use highlight. It's a device that store and process data. This sounds like a calculator, right? But the difference is it also process the data according to the instruction given in a program. It basically means that it's a machine that processes the data based on your program. Right? It's as simple as that. And that's a computer. So if you look deeper, the hardware side, you have logic gates, control signal, and storage, right? Things that do computation, add, subtract, multiply. You have control signal to figure out, okay, in this instruction, you are supposed to add 2 things. Then you do subtract. Then you add another things. And then you have the storage elements. DRAM, SSD, hard drive. Think of the storage elements as your scratch pad, right? In Thai, basically, this is like กระดาษทดนะครับกระดาษทดเวลาเราทำโจทย์เลขเนาะเราก็ต้องทดลงไปในกระดาษ storage เนี่ยมันก็เหมือนกระดาษทดของเรา and then physically if you kind of zoom in even further, right? You have things like transistor, capacitor, resistor, and wires. So it basically means there's a bunch of bits that when you put together, it means something to the programmer, right? So what do I mean by that? You have the processing elements. These are your CPU. Right? These are your CPU. Or this can be your GPU. This can be your, basically it's a processor. The processor would have data part. Data part is a hardware. And then the control signal is a control signal that control the hardware. So these are all in the CPU. What else are in your machine? If you look at your motherboard, the other important thing is the memory. You have to put in DRAM. Okay, this is really, really important. And then you have the I/O, which is the storage devices. Hard drive, SSD, your keyboard, your monitor. Right? That's where user interface with the CPU and the main memory. The way data flow is the processor would talk to the memory, right? Data would go between CPU, DRAM, CPU, CPU, DRAM. The I/O would go also into the DRAM. You put the program in there. You put the data in there. When you run the program, your executable actually get copied over from your hard drive to your DRAM, and you run it, right? And today we'll go back in time and look at the history of digital computing. So we're gonna go sidetrack a little bit. A lot of this stuff is for the historical context. But let's look at the dawn of digital computing. It's actually been around for a long time, right? Anyone here heard about this Jacquard's loom before? It looks like this. Anyone want to take a guess? What is that thing that I'm circling? What does it look like, actually?
Is it a punch card?
It does look like a punch card, right? It does look like a punch card. It's actually a card with a bunch of holes. A loom is a machine to put together threads into clothing. So translate that into Thai มันคือเครื่องทอผ้าครับเครื่องทอผ้า loom คือเครื่องทอผ้า Jacquard's loom เนี่ยมันจะเอาไอ้ punch card ที่เห็นในรูปมาสร้างเป็น pattern. So basically you can program this punch card so that the clothing that come out of the machine have different pattern, right? This is one of the earliest example of programmable machine. It's a programmable machine. And if you use GPU and if you program in GPU before, you're gonna see some terminology here that are similar to what the GPU is using. Why is that the case? Well, obviously this thing is called a thread, right? And this is a common terminology. A thread is a running process. Essentially, it's a part of the running process. So one process can have multiple threads. And in GPU, a group of threads is called a warp, which is this thing. That's where the word warp comes from, because it does process a bunch of threads together at the same time. So this is one of the kind of like the earliest example of computing, right? And then anyone hear about the machine ENIAC? So what is ENIAC, if you heard about it? I'm sure some of you might have read about this sometime before. Anyone here know what it is?
The first computer.
Yeah, it's the first computer, right? So this is the picture of the real machine. This is a machine at the University of Pennsylvania. I had a chance to visit that building when I was 15 years ago, a long time ago. And so sorry about the color that really discolor into yellow. But if you look at this machine, you see that it consists of a tons of vacuum tubes, and it weighs a lot, right? It's a huge machine. It's programmable using this 3,000 switches that you see out here, right? That you see right here. Okay, let me change the color of my pen, right? So these are how you program. You just connect the switch together and then you run. This is one of the earliest high performance computing that you have in the world, right? So this is one of the machine in the 40s and 50s, right? in the 40s and 50s, in 1940s and 1950s, there's a lot of hardware advances. There's a machine called ABC, built by Atanasoff and Berry. There's another set of machines built by German called the C3 and C4. This built by Susi, which is one of their earliest computer engineer / architect. Fun fact, these machines get bombed by the Allies during the war. So you can see that these are the machines that to be honest, some of them are used for the war. Anyone here watch the movie Imitation Game before? So if you watch the movie Imitation Game, you will see that in the movie, the lead actor who played Alan Turing, they were basically building this machine. Do you know what's the name of that machine? So the machine name is actually called Bombay, right? And what do we use the Bombay for? Or what did they use it for, I guess?
To solve Enigma.
To kind of crack the Enigma code, right? Basically, is one of the machine that being used once you have some leads based on the ciphertext that the Allies receive, right? The team of engineers and scientists would basically run that ciphertext on the machine, and because the way the ciphertext, I'm not a cryptography guy, but if I remember correctly, basically the Enigma machine, the way the ciphertext work, there are some common letters which basically kind of translate to alphabet. So it's not uniformly distributed. So you can guess, oh, that's a letter Q, that's a letter C. With that, they run it on the Bombay machine to actually decrypt the text, right? So once they decrypt the text, they send it to the military, and basically they would base the operation on these decrypt texts, right? So you can see example of this in real life, and the recreation of this used in the movie, right? So that's the color. And then the Colossus. The Colossus is actually the machine that come after. So basically, I think what happened is German also come with a different ciphertext. So their English built on a machine to crack that particular pattern of ciphertext. And then you have the ENIAC. This was again developed in the University of Pennsylvania. Consider one of the first digital computer. The keyword is digital computer, because if you watch the movie, again, I'm going to refer back to the Bombay machine again. You see that things are moving, right? It's a lot of mechanical parts. The difference between that and the ENIAC is in ENIAC, everything is digital. That's why people consider this the first machine, the first computer, because everything is digital. Everything becomes a digital signal. And then the EDVAC, built by von Neumann, followed by the EDSAC from Wilkes. The EDSAC is where you have the first store program. What does it mean? First store program means that you can store your program in the main memory, which is exactly how we run computer nowadays. Let's look at the way things run. The model of how things run was actually being developed back in the 50s. Right? This is why the invention back in there is so important, because we still use it nowadays. When you run a program, say when you launch Microsoft Word, when you launch Adobe PDF, when you launch Steam to play certain games, right? If you're old like me, you can play like, I don't know, Age of Empire. If you are your generation, you can play Cyberpunk and newer games. Those programs are being stored in DRAM. That's why when you have thousands and thousands of tabs on Chrome, on Google Chrome, that's why you run out of memory. And that's why your computer gets really slow, because every single program that you're running are stored in the main memory based on the same idea invented in the 1950s. And then you have the machine by Bigelow, and then afterward, there's an emergence of software. Fortran, which is one of the earliest language, is invented in 1954. And then from that point on, it turns into the age of Moore's law. Anyone here know what's Moore's law? Just looks like this. Anyone here heard about it before? Yes. พานุเทพครับ All right, you heard about it. Can someone tell me what it is? Can someone repeat that line? So basically, it's not exactly a scientific law. This is an observation by Gordon Moore in an article called Cramming More Components onto Integrated Circuits. This is back in 1965, right? So Gordon Moore, who owns Intel, right? He looked at the number of transistors on the chip that Intel created, and he saw that, hey, every 2 years the transistor on the integrated circuit doubles. So he plot the trend, as you can see on the right side here. It just turned out there's seems to be a linear relationship, right? So you kind of can double the number of transistors every 2 years. These days, it still kind of follow that pattern, with a little bit of the slowdown, because I mean it's hard to kind of make the transistor smaller, right? And it's also from the circuit point of view, given the same area, it's hard to cram things in, right? But it still kind of follow the trend. And this age of Moore's law, as you can see from the left side, you can see that from 1962, 1965, 1970, you can see that things double. And this goes on until now, even now, right? Someone even joked that because he kind of owns Intel, whatever he say becomes the law because the engineer there have to make it because they were getting paid by Gordon Moore, right? But joke aside, we still cram more things into the integrated circuits. So you might be asking, what's the benefit of having more transistor, right? So you know program want to be faster. And you now know that, okay, we somehow have the ability to pack transistor onto my integrated circuits. So why more transistor? What does it give you? Program obviously want more performance. Think of transistor as the resource to address the performance bottleneck, right? Anyone here play Minecraft before? So you all, if you play Minecraft, right? It's a game. Think of it as almost like a digital version of Lego, with a more fancy way to build things. Right? It's an awesome game, by the way. If you play Minecraft, you will realize that you start with certain resources, right? What are these resources that you're gonna get?เพื่อนๆที่เล่น Minecraft บอกรีสอร์ทที่ผมสามารถขุดได้ตอนแรกๆมีอะไรบ้าง
ครับเป็นไม้ครับ
ดินต้นไม้ผลไม้อะไรก็ได้ถ้าผมบ้าหน่อยก็ไปฆ่าวัว ก็ได้เนื้อมา อะไรแบบนี้ใช่ไหมso basically these are the basic resources, and what do you do after you collect these things? เก็บมาแล้วทำอะไรต่อฮะสมมติเก็บเสร็จในเกม
ไปคราฟของใหม่
Yeah, so basically you built something, right? You built the tools to allow you to craft even new things. So while this is not the direct translation or direct good analogy, but think of a transistor as the basic resources that you have. And you can build things from the transistor. You can build adder, multiplier, SRAM, cache, DRAM, you have a choice of, oh, okay, I need more registers, so I'm going to build a bigger register file. I need more cache. I might want to use transistor to build more caches. If you don't know what cache means, that's okay. We're going to cover everything here that I just mentioned. Right? Today, we'll talk about the motivation, why we care. We use transistor as the resource to build awesome things on the chip so that we can have the CPU or the GPU or the memory that are faster. Rinse and repeat. Right? Rinse and repeat. So one of the readings I put in on the recommended reading is actually from Yale Pat, the same guy again, my advisor. What do we call that? I guess not grandfather, but like grand advisor. He has a paper in the Proceeding of IEEE in 2001, right? He wrote a paper called Requirements, Bottlenecks, and Good Fortunes, Agents for Microprocessor Evolution. The paper itself talks about, right? This is a position paper. The way he writes it is he predict what's going to be a hot topic in the future based on the past. So he analyzed the bottleneck, he analyzed the requirements, he analyzed certain assumption that's going to become true. He analyzed certain limitation of the program and the limitation of the CPU. And then he lists topics that are going to become important in the future. And that paper is in 2001. One thing for sure that can be really interesting is because this is a paper exactly 20 years ago. If you read the paper, you might notice a lot of that comes true. He somehow predict what's going to happen about 10 years afterward. Anyone remember 2000? Where we have a single core Pentium processor? Like I think what is it, Pentium Pro or Pentium 2, right? Oh, am I too old? I'm sorry. I make myself feel old. But back in around 2000, it's still our single core processor. World is simple. What's the clock speed? The more clock speed you have, the faster is the CPU. Can I use a clock speed alone to tell whether it is a good processor or not nowadays? How many of you got confused by what processor should I buy for my computer? Because there's so many options, right? Me too. So I need to actually read the specification and I need to figure out, right? And look at the benchmark and look at the many things that compare the performance. Because I mean, back in the day in year 2000, things are simple. What's the clock speed? Single processor. Then in around 2004, 2005, you start to have multi-core, dual core, quad core, these days 8 core. In the GPU, you have 30 different SM or the core as we know it, right? I'm not going to talk about CUDA core. I kind of hate how NVIDIA PR team did that. It's not a real processor. It's not a real core. And GPU has its own core too. We'll go into the detail on what they mean in, I think, lecture 13 or 14, around that. But the paper talks about the evolution of how we utilize a transistor in a different way to make a faster machine. And we still do it nowadays. In modern computer, you have things like the Raspberry Pi, which, to be honest, I'm also thinking of buying one for my own house, right? So that I can watch the TV with the VPN on. You can buy a fancy GPU, right? You can have a cluster, a supercomputer. This is a picture from the cluster at the Lawrence Livermore National Lab in the US. You can have this is the older version of iPhone, right? It doesn't look like this now. It's actually way more powerful. Fun fact, if you own the recent iPhones, the processor there is crazily powerful. It's likely to be more powerful than many laptops that you can buy. You can have something like GoPro, right? What's the good thing about the GoPro versus everything else I show here? What are they good at? Or why would I want a GoPro? So let me rephrase the question. Can I abuse every other machine I show here the same way I abuse GoPro? The answer is no, right? It's like these are machines that are designed to be hopefully more reliable to physical abuse, right? So you can have many types of modern computer. Anyone want to take a guess what's this? This is another computer.
quantum computer.
It's a quantum computer. Thank you. So this is a image of a quantum computer, right? This is another sample of modern computer. So now it's actually pretty exciting because you can have different type of computer, unlike back in 2000 where everything looks the same. CPU. What's the clock speed? How do you make the clock even faster? Now you have, okay, I have the CPU. Is that good? Should I buy a GPU? Should I buy a server? Or should I go with embedded processor? In IoT, I have 10 different devices connected, right? How do I configure them all? Quantum computer, how do I even program this thing? It doesn't even have a proper ISA. So how do I program it? How do I control error, right? No one knows. No one knows the best solution yet. It's all in research. So it's a really, really good time to be a computer architect, to be honest. It's kind of fun. But that's bias because I love it. So what happened if you kind of dig deeper? What happened when I run a program? So let me write a really simple program. Int I equals 10, j equals 20, k, and then I do k equals I plus j. Right? Something really simple. When I run this program, this basically starts from the program itself, right? And then it gets compiled. When you compile that, what do you get out of that? So when I compile the program, what will I get as an output? ผม compile โปรแกรมเสร็จแล้วได้ไฟล์แบบไหนมา It's a binary, right? Yes, awesome, thank you. So it's a binary and it's a file on your computer, right? Unless you run it, it's just another file on your computer. It's sitting there, not getting run. When you run it, what happened is the OS take the binary, put that in the main memory, and tell the runtime system saying, hey, run this program. Then the OS would kind of pick which program at that time will get run on each of your processor. We'll talk about this in lecture 14 and 15 when you talk about multiprocessor and multi-threading. But basically the OS would pick, okay, CPU 1 is empty, not running anything. So go ahead, run this binary. When you run it, when the program is actually running, the binary is in the format that the computer understands. So this is going to be our second lecture. So next week, we'll talk about the ISA and how do we design an ISA, right? So with that, you have the ability to talk to the computer so that the actual hardware or the microarchitecture. So this is the majority of the first half of your course. From lecture 3 onward, we'll talk about the microarchitecture and see why and how we can run things and how do we make it even faster and faster and faster, where we're going to meet with the current technology, or somewhat current technology. It's not the current technology, but close enough. And with this, I will kind of wrap up the lecture with the programming model, right? One of the most important programming models called the way you run the program is the von Neumann model. Von Neumann model. This is built for a store program computer. It has two main properties. When I talk about these properties, think about whether that's true or not with every single program you are writing so far. The first property is instruction are stored in a linear memory. And the memory is unified between instruction and data. And the control will figure out, is that a program or is that a data? Is that true? Can I, if you write code in C before, can I have function pointer? Does my, yes, right? So does my function or my program has some location in the main memory? I can have a pointer that points to that part of the program. That's why I said program are stored in the memory, right? And again, memory is unified because can I have a pointer to my data? Again, yes, I can have every single program data inside my main memory. So basically it means that memory becomes the center of, well, I was about to say center of the universe, but it's not the case. It's actually kind of the center of all the communication. You have program in there, you have the memory in there, you have the program data in there, right? The next important thing is the way you process the instruction is sequentially done. What do I mean? One line at a time. When you convert everything to assembly, how do you run the program? Let's say you're at line N. At line N, what's the next line you're going to run? If you're running line N right now, what's the next line of code that you're running? N+1, right? You process one line at a time. You're at line N, then you do line N+1, then line N+2, N+3, N+4, N+5, blah, 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 blah. This is called sequential instruction processing. Is that a nice property? So let me ask you this. What if I come up with a program that after you finish line N, you jump to random lines? That would be chaotic, right? So von Neumann model kind of simplified the process of writing the program by saying, hey, the way you write a program, after you finish line N, you're going to continue with line N-1. That's how you can tell the computer what's the next line. You are going to have this thing called program counter, which identify, okay, we're at line N. Program counter basically point to the current line so that you can point to the next line, next line, next line. What is the only few exception of when you go to line N, you don't go to N+1? Does that ever happen in your program that you're writing? So can I go line N and then maybe line N+20? All right. Anyone here write a code with if else or loop? Right. So basically, if you have a code with if else or a loop, it basically means that sometimes you go to line N+1, sometimes you go to the other different line. That's because you have what we call control transfer instruction or branches. These are branch in code that you basically have to pick. Are you going to that instruction or the other instruction, right? So this basically encapsulates the von Neumann model. And the way it works in the hardware is kind of simple. You have this is the ALU, this is your DRAM, input and output. Input, it can be your monitor, mouse, hard drive, network port that listen to new packet coming in. You can have the program counter and register in the control unit. You expand into this design in lecture, I think 5, actually 4 or 5. Then everything here, inputs go into the main memory. The von Neumann model dictates that the PC over here, the program counter, tells you which line in the processor you're processing right here, right? Data and address, so that you can process your data. Then, is this the only model? So can you guys give me 1 second? I think someone is in the front of my house with the delivery. I'll be right back. Okay, I'm back. So is this the only model? No. Anyone here program in a functional programming, use functional programming before? Like Haskell or Scala or even Rust? So if you program in functional programming before, it's kind of closely a different model. Von Neumann is not the only model, but it's one of the most dominant. What do I mean by that? It means that major instruction set architecture, or the ISA, use this model. x86 use it, ARM use it, Power, IBM Power use it, MIPS use it, even RISC-V, which is another new ISA, also use it. What is the alternative? The alternative is called the data flow model. Von Neumann say instructions are fetched and executed in the control flow order. It follows line n to line n+1 to n+2 to n+3. Instruction pointer would grab the next instruction. Is actually mostly sequential, except when you have if else or for loop, right? The data flow model is different in the sense that the instruction is fetched. In the data flow order, it computes when the operand becomes ready, and you don't have instruction pointer, right? And I'm going to show you an example to make it more clear. But the ordering of what you run will be based on the data itself, not the structure of the program. Think of this as a math function. You can simplify this by think of the data flow model as a math function, right? If I have f of x and y and c, when can I run this function f? Can I run it if I know x and I don't know y and z? Can I get the results with that? No, right? The only time you can start to get the result is if you know x, you know y, and you know z. You need to know all of them. Once that's available, one of them are available, you can run anytime, right? So that's the data flow order. That's the data flow order. You're gonna be able to execute this function once you know the input value, right? Many instructions can execute at the same time with the data flow model. So this gives you parallelism. This is one example. The left side, sorry about animation bug. This is sequential of von Neumann. You have a code C equals A plus B, X equals B multiplied by 10, Y equals B plus X, and C equals C plus Y, right? Converting the same thing to a data flow model is something like this. You have input A and B and 10, right? What's the first thing you can do? You can both do this line and this line together because C depends on A and B. You know both A and B, so you can do the add, right? X requires B and 10. You know both of them, so you can do the multiply. So you can do both add and multiply at the same time. Then you know that, okay, once I have the result of x equal b minus multiplied by 10, I can then run this next line, which is y equal b plus x, which is this thing here, right? So you do y equal b plus x. Once you know y, then you can run the last line, right? Let me ask this question. As a programmer, which one is easier to write? The sequential or data flow? Sequential, right? It's simple. It's like do this, followed by this, followed by this, followed by this. Because I guess as a human, it's much easier to process things one thing at a time, right? But which one is faster? So let's assume each line here take one cycle. How many cycles does it take to process a sequential program with von Neumann? If each line here is one cycle, 4. What about data flow? 3, right? Because you can do the add and multiply together. So in that case, it takes 3 cycles. So the left side slower but more natural. The right side is kind of weird but faster, right? So let me ask you one last question. Would it be good if I just assume you can program this in the von Neumann model? I don't care. You program in a von Neumann model. But inside the hardware, I'm going to process that in a data flow model. Is that good? This sounds good, right? Basically, from the programmer point of view, I don't have to think about this weird data flow model. But I'm going to get the benefit of data flow because the hardware do this for you. Fun fact, your CPU does this. Your CPU does this. GPU doesn't do this, but the CPU does this. There's a lot of transistors dedicated to making sure this is done in the data flow model. We call this out of order scheduling. We will talk about this and learn how this is done in, I think, lecture 7. So this is another thing that the hardware can deliver for you. You assume certain abstraction in the software. With the abstraction, we optimize it in hardware to make sure your life is good. Performance is also good, right? So if you talk about data flow, let me expand a little bit this topic a little bit more. You can have multiple types of data flow node. You can have computation, conditional, relational, and barrier, right? You can have if else. You can, once you have the if else, right, which is conditional, and you have true and false, you can use that and to generate this, right? No, wrong direction. You can have the result that compare things, send in as the condition, so that you can forward value to many places in your program. So let me show you one example of a data flow program written in the diagram, right? My quick, it's not going to be your homework, but it's good to think about because the lecture is already posted, right? So I'm going to show you this diagram. Hint, do the left side and the right side separately. But next lecture, once we begin, I'm going to talk, what does this data flow program do? So this is a real program. It does certain tasks. The left side is kind of looping and counting up. The right side is also looping, but it's doing something else with the input. So feel free, if you have time, take a look at this and you can kind of figure out, if you have time, to see, okay, what does this thing do? How about I give this an extra credit for people who try this for next lecture? And I'll give you 5% for assignment 1. This is fair game. Take a look at this. If you want to tackle this, And if you get it correctly, you get 5% additional on top of your assignment 1 grade. Sorry. All right, so this is one example of data flow program. And this is actually the last slide for the class. I have a few more things, which is like kind of before we go. But before I go through this, any last minute questions about the material we've gone through so far, or any curiosity questions that I can answer?
I heard you mention about the functional programming. Is that related to data flow paradigm?
So I would say it maps really well with data flow, because the way functional programming works is whenever inputs become ready, you can run that function and the function gets triggered right away, right? So that's kind of like the same way you execute data flow program. That's why I said they're related.
Thank you.
And if you try functional programming before and you compare that to like C or Java and Python, you might realize that it can be tricky to program, especially for the first time. อันนี้ตอบคำถามเมื่อกี้ปะครับหรือว่ายังไม่ค่อยเคลียร์
ครับก็คือผมไม่เคยเขียนฟังก์ชันนอลครับแต่ว่าเห็นอาจารย์เมนชั่นว่ามันมี benefit กับ data flow paradigm ครับก็เลยไม่แบบรู้สึกไม่เข้าใจ
คือวิธีเขียนมันจะคล้ายๆกันนะฮะคือ functional programming เดี๋ยวผมขออนุญาตอธิบายภาษาไทยเนาะfunctional programming เนี่ยมันคือการเขียนโปรแกรมโดยที่ convert ทุกอย่างเป็นฟังก์ชันแป๊บนึงนะครับแมวมันขโมยอาหารนี่ครับคือมันจะเป็นการ convert เนาะเป็นการ convert ตัวโค้ดเราอะให้มันกลายเป็นฟังก์ชันหมดเลยแล้ว input ของฟังก์ชันอ่ะมันก็คือเหมือน input ของฟังก์ชันปกติในพวก C หรือ Python แต่เราจะไม่ใช้ loop เราจะใช้ recursion ก็คือเป็นฟังก์ชัน call ไปเรื่อยๆคือฟังก์ชันมันจะเป็นเขาเรียกว่า first class citizen แล้วก็น้องควรจะเลิกกินอาหารคนแล้วก็เวลาเรารัน functional programming เนี่ยอย่างหนึ่งที่เราจะได้มาด้วยความที่มันคล้ายๆกับ data flow เนี่ยเราจะเห็นได้เลยว่าโค้ดตรงไหนสามารถรันเป็น parallel ได้เพราะฉะนั้นมันก็จะ potentially คือมันจะสามารถได้ performance ที่มากขึ้นได้เห็นไม่น่าจะคือมันต้องลองเขียนดูด้วยก็เลยเดี๋ยวไม่งั้นเดี๋ยวคลาสหน้าถ้ามีเวลาเดี๋ยวผมเอาตัวอย่างของ functional program มาให้ดูว่ามันเขียนแล้วมันออกมาหน้าตาเป็นยังไงดีก่อนไหมเอาไหม
ขอบคุณครับ
โอเคมีใครมีคำถามเพิ่มไหมครับ All right, so if there's no more questions, I guess before we go, let me kind of introduce things that I'm working on and also other stuff. So first of all, this has already been awesome. So I appreciate what you've done so far. Dealing with online lectures is not easy. So I want you to ask questions either just by raising your hand or type it on the chat. I really appreciate that, because that would tell me, am I going too fast or am I going too slow? That's how I can gauge whether I should go faster because you're bored, or should I go slower because no one understands what I'm saying. The second thing is Lab 1 would be available soon. I think it's already available if I recall correctly, but I might be wrong. The starter code is up. The material, the actual text that I've written, I might have the due date wrong. It's due actually, let me put it 3 weeks from now. So I'm going to give you a lot of time to work on lab number 1. So if you have questions about lab number 1, let me know. It's actually, again, once you know what you have to do, it's basically a bunch of if else and switch case. It's actually pretty simple once you understand what we want you to do. And then before we leave, we do have about 30 minutes. So I'm gonna introduce a little bit more about my own work in case you want to work on certain things here for your pro. น้องไม่กินข้าวคนน้องก็มากินทิชชู่ขอโทษนะครับ so that in case you want to do certain things on the project and if the research area that I have kind of match your interest, let me know as well. So here is some of my research area. So I look into how to design virtual memory for modern workloads. I have multiple papers to the top tier conference. The last paper at PAC 2020 was kind of targeting all type of system that want to utilize huge page. There's also a paper that I collaborate with the team at ETH Zurich on how do we design a totally new virtual memory design for the CPU machine, right? This at ISCA 2020. And I have a couple of works on how to design a virtual memory for GPU. These are published at ASFLOS 18 and Micro 2017. I also look into GPU design. As I said earlier, I kind of like have the motivation coming from I play a lot of games, right? So I want to understand how the GPU works. So I have works to improve the performance of the unified virtual memory. So if you program in GPU before, you might have realized one thing you can do is instead of calling CUDA malloc, then CUDA launch, and then CUDA malloc, CUDA memcopy, CUDA launch, then CUDA memcopy back, and then free the memory. You can do CUDA malloc manage. That would trigger unified virtual memory to kick in and would manage the memory that you allocate for you. It can be on the CPU side. It can get automatically migrate to the GPU side. The downside of that is not perfect. It actually can be pretty bad in certain scenarios. So we are looking into how to make it better, especially under the assumption that you don't have enough of the GPU memory. I also look into how to manage GPU concurrency so that you can have basically a faster GPU, how to improve GPU efficiency in certain way, both on the core architecture of the GPU, as well as how do you design a GPU that would be low power and also high in performance. What else? I also look into DRAM design. So these are the topics that I look into because many of my friends, including my advisors, mainly working in how to design a better memory, right? Better DRAM, better non-volatile memory, and new types of memory. So I look into how to make DRAM even faster. I have work that involve processing in memory and how to enable processing in memory to make sure that things that you're running on the CPU is coherent. Basically, the data is the same copy with the one that's running on the processing memory. I also look into hybrid memory. What if you have a mix of the DRAM as well as a non-volatile memory? Can we have a memory that would be 2 terabyte or 3 terabyte in size, but behave and in terms of speed and reliability is as fast as your DRAM? I also look into network on chip a lot before I migrate to looking into GPU, because to be honest, network on chip was one of the popular topics back around 2008 to 2012. In fact, if you look at the CTO of NVIDIA, Bill Daly, he actually has a lot of work on that area as well. It actually governs how do you actually manage communication between the CPU core as well as the memory as the core scale. As you have more cores, more memory locations that you have to access. So I have the design to provide energy efficiency as well as scalability. And then also how do you handle faults when some of the link goes off, right? How do you correct that? How do you actually make sure things still behave normally? What else? I looked into accelerated design. So this is an example that I said earlier about DNA sequence alignment in memory. I also have another separate work just presented in July on how to do machine learning computation on RAM, resistive memory. So this is a new type of memory, which turns out the way you read data from RAM is you are doing exactly matrix multiply. So you can actually now organize the data in a different way so that you can do matrix multiply within this RAM, right? I also have a collaboration with a team in Hong Kong to look into, also Huawei, to look into storage and file system in mobile devices. So we have a paper to Usenix ATC, a poster to FAST 2020, and we also have in a few upcoming work that are being submitted right now on how to actually make a better storage systems for mobile phone. How can you design a better system software for mobile phone so that you don't see the lag, you don't see the performance drop. I also have the look into high performance computing. So this paper just got accepted to Micro 2021. So we got the results back last month. So this is basically on how do we come up with the new design in graph processing. So we came up with the new ISA so that we can enable processing in memory. So hopefully that also partially answer your question that you have about how do you interface with new hardware design. So this paper extends the current ISA to include set operation that will be done entirely in memory so that you can do set operation to accelerate graph application. Basically, we represent graph in a set, which means that if you want to do something with your graph, it turns into union, intersection, and differences. So it makes your operation much, much faster. Right? So that paper is going to be published in Micro 2021 in October. What else am I working on right now? So I'm looking into how do you design system for large scale federated learning? How do you accelerate container design? How do you find out what type of data structure is related to each of the data that you're accessing right now, so that you can have a system from the programmer point of view, giving hints that, oh, this is an array, this is a linked list, this is a graph, so you can optimize the hardware differently. I have been looking with the team in Hong Kong to look into how to do a page cache or file system design for mobile phone. I look into garbage collector design for mobile system. This is also in collaboration with Huawei in Shanghai. There's also a project on, there's a new material where now instead of having the processing in memory, you can attach the memory directly next to the CPU. This is called monolithic 3D integrated circuit. So everything is now 3D, the whole thing, the whole package. So we look into how to architect that. So we just submitted a paper on some sample. Basically, it's more like analysis and also a few case study on how to architect that. We also look into accelerated design for deep learning and DNA sequencing to follow up some of the work we submitted. Also high performance hardware design for graph application, disaggregated memory for SoC and IoT application. So this is done with my PhD student, who actually was a PhD student at University of Sydney. He's currently visiting my lab right now, and we are working together on one of these topics. And also resource management for CPU, GPU architecture. So this is a collaboration done with some of my friends in China right now. So I have a few ongoing collaboration with CMU, Intel, NECTEC, UT Austin, ETH Zurich, Chulalongkorn University. To be specific, it's actually with my wife on the bioinformatics side. She is a doctor in a medical school, so we have a few projects together and still cooking up. So it's not like fully blown, like we know exactly what we're gonna do yet. So we're still like kind of brainstorming. I have a collaboration with one of my friends in UIUC, also with team from City University of Hong Kong and Huawei. Also, the work that do machine learning in RAM, resistive RAM, that's in collaboration with the team from UC San Diego. The student now has graduated and moved to TikTok, actually in the US. I have another student that I'm working with closely from Shanghai Jiaotong PhD program. We are looking into how to accelerate graph application. So have a few projects with Wuhan University of Technology, National University of Taiwan, and also this another separate project on how to make sure the GPU driver can send data amongst itself rather than going back to the CPU, so that when you have a huge deep learning workload, you don't have to bounce the data around between CPU memory and the GPU memory. So you can actually extend your own local GPU memory to a neighbor GPU. I also have another collaboration with National University of Defense Technology in China. This is mostly on the GPU architecture side. I also have collaboration with VMware Research, as well as UVA. So for the collaboration with UVA, I'm working with one of the students who wants to design a virtual memory for processing in memory. How do we actually integrate that and make sure it runs together with the CPU? So I basically I want to, sorry about this. I should have checked this. Sorry, guys. So I also teach the same class at TTGS, which is where I have to work. Well, I got the Thai scholarship, so I have to work at TTGS for like 20 years based on my contract. So this is where I mainly at. I'm teaching computer architecture class right now as well at TTGS. So I got confused and typed in this. But welcome to ComArt class at WizTech, guys. Any last minute question? So that's all for the class. So let me switch back to Thai so that in case you want to ask question in Thai, you can do. มีคำถามไหมครับ
ถามเรื่อง
ผมมีหนึ่ง
อัน
คำ
นี้
ถาม
หาจากไหนอะครับ
สักคนก่อนครับพอดีเป็น2 คนพร้อมกันอันนั้นลงลิสต์ก่อนนะลงลิสต์
โอเคครับ คือผมไม่ค่อยคุ้นเกี่ยวกับคอมพิวเตอร์อาร์คิเทคเจอร์ครับผมมาจากคณิตผมก็เลยอยากรู้ว่ามีอะไรที่อยากจะให้รู้ก่อนมาเรียนในคาบนี้ไหมครับ
คือผมจะ assume ว่าเด็กประเทศไทยทุกคนไม่รู้คอมพิวเตอร์อาร์คิเทคเจอร์เพราะว่าเป็นสิ่งที่เป็นท็อปิกที่หลายๆมหาลัยไม่ค่อยสอนเพราะฉะนั้นผมจะเอาแบบ ground up เลยคือถ้าอยากจะให้รู้อะไรตอนนี้ก็คือให้รู้ว่าเขียน C เป็นใช้ C เป็นภาษา C เนาะแล้วก็ใช้ Linux เป็นอันนี้คือ minimum requirement แล้วถ้ามีคำถามอะไรผมขออย่างหนึ่งว่าช่วยยกมือแล้วถามเลยเพราะว่าไม่งั้นมันจะไม่เข้าใจเพราะว่าหลายๆอย่างที่เราจะพูดมันจะ build up ไปเรื่อยๆปึ๊บเพราะฉะนั้นถ้าเราสมมุติตรงกลางแล้วเราเริ่มแบบไม่เข้าใจอะไรตรงกลางอ่ะแล้วถ้าเราไม่ถามตอนนั้นอ่ะมันจะไม่เข้าใจไปเรื่อยๆเพราะฉะนั้นผมก็จะขอย้ำอีกทีหนึ่งว่าอาจจะต้องรบกวนว่าถ้าเริ่มไม่เก็ตอ่ะแบบถามก่อนเลยหรือแบบบอกให้ผมอธิบายสไลด์นี้อีกรอบเนี่ยเป็นเรื่องปกติมากโดยเฉพาะออนไลน์คือช่วยบอกเลยว่าสไลด์นี้ไม่เก็ตครับอาจารย์ขออีกรอบอะไรเงี้ยได้เลยน้องพารากรเดี๋ยวผมจะแสดงว่า assignment 1ผมยังไม่ได้ publish มันแน่เลยเดี๋ยวผม publish เลยแล้วก็จะได้เห็นว่ามันมีอะไรบ้าง starter code คืออะไรเมื่อกี้น้องอีกคนหนึ่งที่ถามพานุเทพอะครับ
ครับที่ต้องใช้ Linux นี่เพราะว่ามันมีโปรแกรมอะไรที่ลงได้เฉพาะใน Linux หรือเปล่าครับหรือว่าใช้ Mac
คือ build จริงๆแล้วถ้าจะใช้ VM ก็ได้คือแค่แบบโค้ดที่เป็น skeleton code ที่ให้มันจะ build บน GCC อ่ะ คือชีวิตจะดีขึ้นมากถ้าอยู่บน Linux เท่านั้นเองครับ
โอเคครับ
WizTech เขามีเซิร์ฟเวอร์ให้น้องๆใช้กันหรือเปล่าตอนเรียน
มีแต่ว่าไม่รู้ไปบิวอะไรวันนู้นมันจะโอเคหรือเปล่า
โอเคงั้นเดี๋ยวทำใน VM ก็ได้เพราะว่าที่ TG ก็ให้น้องทุกคนทำใน VM เหมือนกัน
โอเคครับ
ครับ โอเคครับมีคำถามอะไรเพิ่มไหมครับ
ฮัลโหลครับพอดีผมชั่วโมงแรกผมเข้ามาไม่ทันว่าผมมีงานนิดหน่อย
มีเพื่
อาจารย์
จ้างแล้วครับเดี๋ยวผมจะพอดีอันนี้มี recording เนาะเดี๋ยวผมจะรบกวนพี่แอดมินสุดใจดีมาส่งไฟล์ให้ผมแล้วเดี๋ยวผมอัปโหลดให้ใน YouTube แล้วเดี๋ยวผมก็เอา playlist เนี่ยไปแปะเข้าไปในคลาสเว็บไซต์อะครับ
ได้ครับขอบคุณครับ
แต่ชั่วโมงแรกไม่ได้มีอะไรหรอกสมมติชั่วโมงแรกเราพูดถึงว่าคลาสนี้มีอะไรบ้างประมาณแบบ assignment กี่เปอร์เซ็นต์ต้องการอะไร expectation คืออะไรอะไรเงี้ยครับ
แค่อยากถามเรื่องไอตัวโปรเจกต์นิดหนึ่งนะครับเพราะอันนั้นคือเป็นแบบว่าเป็นงานเดี่ยวใช่ไหมครับ
เป็นคำถามที่ดีเพราะว่าเมื่อกี้มีน้องอีกคนหนึ่งถามเหมือนกัน up to 3ก็คือเดี่ยวก็ได้2คนก็ได้3คนก็ได้ครับแต่ว่าถ้าเป็น2คนหรือ3คนผมจะ assume ว่าแบบมันจะต้องยากกว่าโปรเจกต์คนเดียวอย่างเงี้ยเนาะแล้วก็ถ้าโปรเจกต์3คนก็ต้องยากกว่าโปรเจกต์2คน
โอเคครับ
ครับมีคำถามอะไรเพิ่มไหมครับ
ครับสไลด์หน้าที่54นี่คือคำถามมันคือหมายถึงให้แปลความหมายของไอตัว data flow โปรแกรมเหรอครับว่า
ใช่ว่าอันนี้ทำอะไร
เอาไว้ทำอะไร
มันทำอะไรกับ A กับ B คือ input คือ Aกับ B แล้วมันหาอะไรระหว่าง A กับ B
โอเคครับขอบคุณครับ
ครับงั้นผมถามกลับบ้างพูดเร็วไปปะครับหรือว่ากำลังโอเคยัง process ได้อยู่
สำหรับผมว่าเร็วไปนิดนึงครับ
เร็วไปนิดนึงเนาะเดี๋ยวถ้าสมมุติครั้งหน้าอย่างที่เจ๊ถึงว่าถ้ามีสไลด์ไหนที่แบบเร็วไปหรือแบบเฮ้ยอาจารย์ใจเย็นผมยังไม่เก็ตเลยว่าสไลด์เมื่อกี้ทำอะไรรบกวนยกมือแล้วบอกอาจารย์ช่วยอธิบายสไลด์นั้นอีกรอบเนี่ยผมโอเคแค่ต้องบอกเพราะว่าถ้าผมรู้ว่าอันไหนไม่เก็ตผมจะได้ค่อยๆอธิบายอีกทีหนึ่งเนาะก็เลยขอรบกวนนิดนึง
ผมขออาจารย์อธิบายสไลด์ให้2ได้ไหมครับพอดี
ได้ครับได้
พอถึงสไลด์นั้นสไลด์ผมค้างก็เลย
โอเคได้คำถามก็คือให้อธิบายนี้เนาะ
ครับผม
งั้นขออนุญาตภาษาไทยเลยแล้วกันเนาะก็คือเรากำลังเทียบ von Neumann กับ data flow อยู่ไอ้ von Neumann น่ะก็คือรันทีละบรรทัดที่1 2 3 4 5ใช่ไหมซึ่งก็คือสมมุติโค้ดเราเกิดเนี้ย c เท่ากับ a บวก b บรรทัดที่2คือ x เท่ากับ b คูณ10บรรทัดที่3คือ y เท่ากับ b บวก x บรรทัดที่4คือ z เท่ากับ c บวก y เนาะอันนี้คือ sequential โปรแกรมปกติไม่ได้มีอะไรพิเศษแต่สไลด์เนี้ยผมแค่จะบอกว่าถ้าอย่างเงี้ยเราจะ convert เป็น data flow เนี่ยทำยังไงเราก็รู้ใช่ไหมว่าอันแรก c เท่ากับ a บวก b จริงมันก็คือ operation บวกที่มันต้องการ input จาก a แล้วก็ b เพราะฉะนั้นถ้าเรามี a มี b มันก็จะเริ่มรันได้เลยแล้วข้อดีของ data flow เนี่ยเรารู้อีกว่า x เท่ากับ b คูณ10ถ้าเรามี b เรามี10เราก็รันได้เลยเหมือนกันเพราะฉะนั้นไอการบวกอันเนี้ยกับการคูณมันรันไปพร้อมๆกันได้เสร็จแล้วไอ้ y เท่ากับ b บวก x มันจะไปรันพร้อมกับเพื่อนไม่ได้เพราะมันต้องรอ x ใช่ไหมเพราะ x คืออยู่ตรงนี้เพราะฉะนั้นเราต้องรอว่าอันเนี้ยพอมัน produce x x เนี่ยก็ต้องรอให้มันเสร็จมันถึงจะเป็นสเต็ปต่อไปแล้วสเต็ปต่อไปคือพอ y เสร็จก็คือ z เท่ากับ c บวก y อันนี้ก็คือคีย์ว่าพอเรา convert เป็น data flow มันคืออะไรเนาะแล้วคำถามต่อไปผมก็เลยถามว่าถ้าเราเป็นโปรแกรมเมอร์เราชอบทำแบบซ้ายหรือแบบขวามากกว่ากันแบบไหนมันคิดง่ายกว่าซึ่งคนส่วนมากก็จะตอบว่าแบบซ้ายมันคิดง่ายกว่าจริงไหมครับเพราะฉะนั้นแบบซ้ายมันจะ natural กว่าสำหรับโปรแกรมเมอร์แต่สำหรับในเชิง performance เราจะเห็นว่าแบบซ้ายมี4บรรทัดถ้าสมมุติผม assume ว่าแต่ละบรรทัดใช้1 cycle 1 CPU cycle ก็แปลว่ามันใช้4 cycle ใช่ไหมแต่ถ้าแบบขวาด้วยความที่บวกกับคูณมันทำพร้อมกันก็จะเลยใช้แค่3 cycle เพราะฉะนั้นแบบขวาเร็วกว่า 25% เพราะฉะนั้นผมก็เลยบอกว่าเนี่ยเดี๋ยวเราจะมาเรียนกันว่าไอ้ CPU ที่เราซื้อทั้ง Intel ทั้ง AMD ที่เราซื้อเนี่ยจริงๆแล้วเราโปรแกรมแบบ sequential ใช่ป่ะแต่ใน CPU มันจะไป convert ให้มันกลายเป็น data flow แล้วมันก็จะรันแบบ data flow ให้เราแล้วเดี๋ยวเราจะเรียนกันว่ามันทำยังไงไอ้เทคนิคเนี้ยในประมาณ lecture 7โอเคครับ
อาจารย์ครับกลับไปที่รูปตัวการบ้านเมื่อกี้ครับสงสัย operation ของกล่องหนึ่งว่ามันคืออะไร
ได้
วงกลมแล้วก็เป็น t กับ f ครับอันนี้คือเทียบว่าเข้ามาเหมือนกันหรือเปล่า
อ๋อโอเควงกลม T กับ F ก็คือว่ามันจะเอา input อันนี้คือ input ใช่ไหมแล้วตรงเนี้ยมันจะให้ว่า true หรือ false ถ้าไอ้ที่เข้ามาเป็น true มันจะ forward input ไปที่พอร์ตที่เขียนว่า true ถ้าเป็น false มันจะ forward input ไปด้านที่เขียนว่า false
แล้วลงกาวก็คือจบโปรแกรม
ลงกาวคือจุ๊บหายไปเลย input หายคือโยนทิ้งปาทิ้ง
อ๋อโอเค
ไอ้ฝั่งซ้ายกับฝั่งขวามันจะจบพร้อมกัน
โอเคครับขอบคุณครับ
โอเคครับมีคำถามอะไรเพิ่มไหมครับ
ตรง example อันเนี้ยครับควรจะ submit ยังไงครับ
อะไรนะครับ
example อันเนี้ยครับที่เป็นงาน extra credit อันนี้
อ๋อ
ควร
จะไม่มี
submit ยังไง
submission เดี๋ยวสัปดาห์หน้าผมจะมาคุยกันต้นคลาสเราจะให้ทุกคนที่มีคำตอบยกมือ แล้วผมก็จะจดชื่อเอา
อ๋อโอเคครับ
ยากไปไหมเพราะว่าผมรู้สึกว่าถ้ามี submission เดี๋ยวมันวุ่นวายก็ต้องมานั่งคอยกด submit เดี๋ยวลืม
โอเคครับขอบคุณครับ
โอเคครับ งั้นถ้าไม่มีคำถาม
XOR นี่คืออะไรครับ
ตัว ไหนนะ XOR อ๋อ XOR ครับ XOR exclusive OR exclusive OR ถ้าไม่แน่ใจว่าคืออะไรรบกวนวิกิเลยครับ exclusive OR มันแปลว่าอะไร ตัวนี้ตัว C ไม่ใช่ตัว U exclusive OR มันก็คือเหมือน OR แหละ แต่ว่าถ้าเป็นจริงกับจริงมันจะเป็นเท็จคือต้องเป็น exclusive อะต้องมีจริงแค่ตัวเดียวถึงจะเป็นจริง
อาจารย์ครับผมมีคำถามครับ
ครับ
ผลการนัดตอบอันนี้เป็นไทยเป็นแบบไทยโคดโคได้ไหมครับ
เป็นอะไรนะ
ผลการนัดตอบปัญหานี้เป็นแบบโคดได้ครับ
ได้ทำเป็นโค้ดก็ได้
ครับผมครับ
โอเคครับ โอเคครับ งั้นถ้าไม่มีคำถามอะไรเพิ่มก็ถ้ามีคำถามอะไรเพิ่มหลังจากนี้อีเมลมานะ แล้วก็นั้นเดี๋ยวผมขอ wrap up lecture วันนี้ก่อนละกัน มี last minute อะไรไหมครับ ก่อนที่ผมจะปิด โอเค ถ้าไม่มีอะไรก็ขอบคุณมากนะครับ เดี๋ยวสัปดาห์หน้ามาเจอกันอีกทีหนึ่ง
ขอบคุณครับ
โอเคครับ
ขอบคุณครับ
ขอถามอีกทีวิดีโอผมอะมันโผล่หรือเปล่าหรือมันโผล่แค่สไลด์ เหมือนผมพยายามจะเปิดวิดีโอแต่มันไม่มีหน้าขึ้นมา ผมต้องรีบูตแน่เลย เดี๋ยวสัญญาว่าครั้งหน้าจะมีวิดีโอ แต่ไม่รู้ว่าช่วยอะไรหรือเปล่าจริงๆแล้ว ก็คือจริงๆก็หลักๆก็อยู่สไลด์นี่แหละ โอเค ก็ขอบคุณมากนะครับ
ขอบคุณครับ
โอเคครับ สวัสดีครับ
สวัสดีค
ครับ รับ